Hi students, this particular lecture is going to be on waves, which is the topics of really chapters 16 and 17 of the book. So I'll explain that in a moment. As I've said in the past, I'm not exactly sure why the book lays itself out like it does. Chapter 17 officially says linear superposition or something like that. I think it's superposition. I think that's the title of the chapter. Superposition is an aspect of waves. And I'm not, again, I'm not really sure why you'd have an entire chapter at this level of class centered on superposition. So there are a couple of concepts out of that chapter I will use. So don't let this intimidate you. Most of this is going to be out of chapter 16. There's going to be some chapter 17 in there, but I pick what's I think is important out of chapter 17, and the rest of it I leave on the table. So anyway, at least what's important for you guys. All right. So the idea is this chapter is about waves. Now, waves, if you look in the chapter, I would say the college physics aspect of it is defined. What is a wave? It's defined as a disturbance that propagates. My eraser. Which is a fancy word for saying or moves from the place it was created. So that's a typical first definition of waves that you'll get. All right, and so for instance, what are some examples of waves in this nature? Well, you might have water waves, caused by maybe wind or a rock thrown into a body of water. So the wind either creates the waves that you see in the beach, or for instance, you throw a rock in the water, you see these nice circular waves. And those are examples of waves. It's a disturbance. The wind is disturbing the surface of the water, causing waves, or the rock, as it lands into the water, is disturbing the water and causing waves. Okay. You could have, that's one example. It's another example. You could have sound waves. So you could have sound waves. Another example. Sound waves caused by the disturbance, or by the basically caused by the disturbance from a change in air pressure perhaps created by an oscillating cone inside of a speaker. So you have sound waves. Sound waves are waves that going through some sort of medium, like air or water or anything. Any medium will have its own speed of sound. Um, Another example of waves is electromagnetic waves. Talk about those in chapter 2. Or sorry, not chapter 2, physics 2. We have another one, it's electromagnetic waves. Another example. And they're essentially well, we'll talk about those in physics too. Here's an example of that. We'll talk about oscillating charges, but I have to tell you what a charge is first. So anyway, there's many examples of waves. So you might ask yourself the question, well, we're going to study two theories in this class, theory of mechanics and the theory of thermophysics. Where do waves fit in? Well, it turns out the waves actually don't fit in any particular theory. In fact, they are ubiquitous. They are across theories. You have waves like the water waves we talked about. That's an example of mechanics. That is an application of mechanics. The sound waves is another application of mechanics. We can maybe say acoustics. Electromagnetic waves, electromagnetic theory. And so you have different reasons for waves. You could have a wave on a string like a violin string or a guitar string. Again, that would go back to mechanics. And so you can have fluid mechanics like the water waves. So you have all these different aspects, all these different examples of waves, and so they really don't belong to any particular theory. In fact, they're actually, when we get into quantum mechanics, we'll find out that they're actually a state of being. That waves are actually exist as a state of being. So, what does that mean? Well, we will find out in quantum mechanics. We will discover that everything in the universe is both a particle and a wave. Everything exists in a dual space, a wave particle duality. So that is where we will take this when we go into more advanced quantum physics. That literally a wave is in its very own nature a state of existence. So it kind of brings into a question: what about a particle? We kind of took the particle, as we took the particle as something that we just assumed, right? But in reality, if you go back to the Big Bang, there were no particles. There's a primordial soup. 13.7 billion years ago, there were no particles, and so you come to ask the question: well, how do things clump together? We take it as for granted that things come in clumps. They come in units. We can go out and say we can look in there. There's a shoe, or there's a car, or there's we have various ways of making things into units. From all the atoms and molecules and make it up, but the question really comes down to is like even in the most fundamental sense, a particle is kind of a sort of a miracle, if you will. I mean, in fact, you can actually have a chapter before all the chapters in this book and just call it particle and just say, how is it true that even a particle exists? So I'll explain a little story here before we go on to talking about waves. So turns out that, the physicists could not answer that question. As you build the universe up, you go back to your periodic table, you start off, you have hydrogen is element 1, element 2 is helium, element 3 is lithium, 4 is beryllium, 5 is boron, and 6 is carbon, 7 nitrogen, 8 oxygen, so on and so forth. The problem is we have no, we can explain, at the time, we can explain how all the other elements formed. Nobody could explain carbon. There's no reason for carbon to exist, which would mean that all life as we know it has no reason to be. And so the question is, well, what? Nobody can actually answer. You know, obviously it seems like an anthropomorphic question because here we are. So how did this come to be? I mean, clearly you have to be able to put together carbon before you can go to the other elements. You know, we have 92 naturally occurring elements in the universe. How do you get past carbon? And so one of the people who looked into this problem was a person by the name of Fred Hoyle. He looked at this problem, and again, it was one of those problems that was defying all the physics. And Fred Hoyle said, you know, there is one way out of this, and that is carbon could form, or carbon might form. He's just theorizing. Carbon might form by 3 heliums basically hanging out with each other long enough to form carbon. You know, 2 plus 2 plus 2 equals 6, right? And now, before, at this point, we had no reason for this to happen. There's no reason for there's no reason for carbon to actually have a reason to form. But Fred Hoyle says the way out of this, the only way out of this, is if an energy level of 7.68 MeV exists for this formation to occur. Okay, if this one energy level exists, and I mean the entire universe, the entire existence of everything is predicated on the existence of this one energy level. If it exists, then we can explain how everything is around. All right, and so he went over to Caltech, and he begged the people at Caltech to perform the experiment to look for this energy level. And there's a new guy, I can't remember his name, he just graduated from Rice University down in Houston, and he went to Caltech and he was looking for a project. So he picked Fred Hoyle's project. And lo and behold, he did all this experiment and he found this energy level. And Fred Hoyle said, you know, that for the first time in his life, his atheism was challenged. That this looked like a fingerprint of God. You know, this energy level is the one energy level that for all that has ever existed and all that ever will exist, this one energy level has had to exist. And this explains really everything that is here. Everything in the universe is based upon the existence of a single energy level. And carbon is the basis of all life. We're talking about, you know, that here, the basis of all life, carbon, exists solely because of the existence of an energy level that nobody even knew about until they looked for it. All right, so even the concept of a particle is not to be taken lightly, okay, in the formation of the universe. So when we go to quantum mechanics, we realize that not only does everything form as particles, they're also waves. Light that we know as a wave usually is actually also a particle. Einstein was able to show that. And then later on in quantum mechanics, things we took as electrons, we actually showed later on that they're actually they're not just particles, they're waves. And in fact, it's kind of a funny thing I'll talk about physics too is that, everybody knows, or people know that J.J. Thomson discovered the electron. Well, it turns out his son, George Pierpont Thomson, or G.P. Thomson as he went by, did the experiment to actually show the electron as a wave. And they said that the father and son both discovered the electron. The father discovers a particle, the son is a wave. It's one of those funny things in physics. There's a number of there's a few father and son Nobel laureates. De Boers, Thomsons, Braggs, a few others. So this is one of those examples. So again, we'll find out that there's a lot to talk about waves, much more so than we're going to talk about in these chapters. All right. So with that said, that's kind of the introduction of waves and existence. Now, with a wave, we're going to find out that we're going to utilize a lot of the nomenclature that we did that we talked about in oscillations. So we have a couple different types of waves. We have two types of waves. Pens seem not to live very long. All right, two types of waves. One is the transverse wave. Another one is the longitudinal wave. All right, transverse wave is one where the propagation direction is perpendicular to the disturbance direction, or direction of the disturbance. Write this down a little further. This is the typical wave that you might naturally draw on your paper. If I ask you to draw a wave, you might draw something like this. You might say, okay, well, I'm going to disturb a string in the y direction, disturb a string, and that disturbance, I'm basically going to move my hand up and down real quick in the string, and a pulse will travel down the string. The disturbance direction will be, say, in the y, and the propagation in the x. So it might look something like a sine wave. Typically, that's how and that's what you might, if I ask you to draw a wave, that's probably what you draw. You'd have a disturbance direction along y, and you have a propagation, a wave would actually propagate. The velocity would actually be going along, the propagation velocity going along x. So the propagation is along x, the disturbance is along y. All right. The other type is a longitudinal wave, as I said. And that is one where the propagation and disturbance directions are aligned. So examples of a transverse wave might be, electromagnetic wave is a good example. Electromagnetic wave is a perfect example of a transverse wave. Another example is a wave on a string. So this would be like a guitar, a wave in a guitar or a violin. A good example of a longitudinal wave would be sound waves. Those are pressure waves. All right. Anyway, running out of space here. Those are two types of waves. So I'm going to start we're going to start talking more about the transverse waves first, like a wave on a string. The mechanical waves are usually transverse waves. And then we'll go into longitudinal waves, which would be sound. Now, water waves are a combination of both. There's transverse and longitudinal characteristics in water waves. All right. And so again, waves don't always perfectly fall into any particular category. I'm just looking at ones that most clearly fall into one category or another. Electromagnetic waves are very much transverse waves. Waves in a string are very much transverse waves. Sound waves are very much longitudinal waves. Okay, so I'm going to erase this. Okay, so let's draw out some nomenclature. So if I were to make a wave, what would it look like? So we'll start off talking about transverse waves. What might it look like? I'll try to draw a good picture. Okay, so you know it goes. All right, so we'll just pretend these peaks are the same height. All right, that's a little bit of improvement. All right, so the propagation direction. So I'm going to try to make some nomenclature here. So we have a wave, and I'll give an example of a transverse wave. We'll talk about those first. It turns out all the nomenclature given for transverse waves will also apply to longitudinal waves as well. So we talk about a wave. Now a wave is a repeating propagations. Oftentimes they're periodic. Which means they repeat over and over again. So what happens is the waveform is the same throughout, just moves in time. So you watch a wave go past you, you'll see the crest. Well, let's see, I watch a wave go past me, let's see over here. I'm gonna see a crest go by me, then it's go down to a trough, then eventually it'll go up to another crest, and then another trough, and so on and so forth. It's gonna repeat over and over and over again. A cycle is a part of a wave, a complete part of a wave, where it goes from one particular instance that you're looking at to return to that same instance. Let's say I want to go, a cycle might be crest to crest. So a cycle is the entire form of a wave, or I would say the entire form of the wave that repeats periodically. So there's a basic form. For instance, I could go crest to crest. I might want to look at my wave like that. I might want to look at, I'm picking apart the crest. Okay, that's a particular aspect, a particular location on that wave. And then the wave's going to do, it's going to go through its entire cycle until it gets back to the next crest. So when I go from crest to crest, I've seen the entire wave. I might decide, well, no, I'd rather look at trough to trough. That's fine. Or you might want to pick a spot on the wave, maybe midway, maybe where it goes through zero, and look at where that same instance of the wave happens again. Again, it's entirely up to you, except that you have to wait long enough for the wave to repeat itself. All right, so we pick out certain nomenclature in a cycle. For instance, the distance from one part of a wave to that part again during its repetition, we call that the wavelength. So the wavelength, again, a wavelength is measured along the propagation direction. So the wavelength We typically give it by the Greek little l called lambda. Lambda. I'll talk about the Greek letter in a moment. Is the length or the distance along the propagation direction. Of a wave cycle. How far do I have to go until I see that cycle again? Until I see that same part again? Whether I decide to go and measure lambda from crest to crest, or if I decide to go measure from trough to trough, it's the same lambda. Or if I decide to measure from this part to say this part, I mean, again, it's the same thing. Okay, so this is lambda. That's the wavelength. Typically, it's given in meters. You might have it in nanometers or something. But again, it's the SI unit. It's a length. Be given in meters. All right. Now, this funny symbol, if you haven't seen it before, it's the Greek letter lambda. Again, we physicists borrow from the Greek alphabet. All right. So this is the L or the little l. The L in the English alphabet, well, lambda, capital lambda looks like an upside down V. And little lambda is a symbol that is wrote above. That's little lambda. So again, both of those are lambda. That's capital lambda. This is small lambda. And we use these Greek letters for various things. We typically use this for wavelengths. Okay. What's another nomenclature? Well, we call the period. The period typically we use a capital T, just like we did back in oscillations, is the time duration of a cycle of a wave. Okay, so how long it took for, if I'm standing here watching this wave, and I say, okay, I'm gonna start my stopwatch. I just saw a crest, and then when I see the next crest, I hit my stopwatch again, or and I figure out how long that took. That would be the period, the time it took the wave to basically propagate it. One cycle is a period. Period T. All right. Now, as far as the propagation velocity is concerned, the wave obviously is going to propagate in the x direction. So we usually will say there's a v sub w, w for wave. And as we just do basic physics here, we go back to chapter 2. The wave's not accelerating. So what would you do? Well, you'd say that v sub w is nothing more than the distance divided by the time. Lambda divided by t. Wavelength divided by the period. Typically, what physicists will do is they like to express things in terms of frequencies. Remember, and we saw this back in our chapter 10 lecture on oscillations. A lot of the nomenclature is going to be the same. Don't let it confuse you. This is something different. These are waves, not oscillation. But the nomenclature is similar. So remember, the frequency in hertz is 1 divided by the period. So typically, the most famous generalized equations for waves is the following. Instead of 1 over a period, I'll just put in frequency. V sub w, speed of propagation, is lambda times f. Okay, this is true for all waves. We'll see this equation again in physics 2. Speed of the wave is the wavelength times the frequency. A universal equation for all waves. So V sub w, for air, let's say sound waves, it is the speed of sound. Okay, VCW for electromagnetic waves. Is the speed of light. All right, so we'll see this again. All waves obey this equation. VCW is lambda F. Notwithstanding, all waves. All right, so I call this usually the universal equation for waves. All right, now, let's do some problems to get our feet wet. Got new nomenclature, new stuff we're studying, so let's do some problems. Okay, I'm gonna look at, and again, on open stacks, they actually lump together the oscillations and the waves. So you're gonna still see some chapter 16 stuff. So open stacks, now we're actually in chapter 16 in our stuff now. So don't let it confuse you. This is open stack, I put the OS. Open stack 16.47. Talking about waves now. So we'll start out basic. Storms in the South Pacific. Travel all the way to the California coast. Which is 12,000 kilometers away. How long does it take them if they travel at 15.0 meters per second? Okay, so we have how far they're going to travel. We have their wave propagation velocity. Okay, and so we're going to go back to some basic physics. I'm going to erase this. So we start off by simply, just like I did a moment ago, the wave velocity is distance they travel divided by the time they travel. Simple as that. Solve for the time. Time will be the wave velocity over the distance. I'm sorry, I got that backwards. X over piece of W. Okay, and then so let's put it in there. So we have, again, 12,000 kilometers. That's going to be 12,000 times 10 to the third meters. We got to get everything in SI. And again, we're told it's 15 meters per second. The time will be 8.00 times 10 to the fifth seconds. Now, I don't know about you, but that doesn't mean anything to me. So I'm going to try to get that into something like days or hours. So I'm going to convert that. So 8.00 times 10 to the fifth seconds. And let's see here. We have an hour has 3,600 seconds. And I get rid of seconds, now I have hours. And then let's say a day has 24 hours. So what's this going to be in terms of days? Well, the storm occurs, generates waves and a disturbance. And it takes 9.26 days to get to the California coast. So some of those waves you might see on the beach in California, maybe have come from a storm in the South Pacific that happened about 9 days ago. All right, so starting off easy. All right, do the next problem. Open stacks. 16.49. This says wind gusts create ripples on the ocean. They have a wavelength. Of 5.00 centimeters. And propagate at 2.00 meters per second. What is the frequency? Wind gusts create ripples on the ocean that have a wavelength of 5.00 centimeters or propagate at 2.00 meters per second. What is the frequency? Again, we're just doing some basic physics to get us started here. So the universal equation of all waves, V sub W is F lambda. Okay, or sorry, I always write it's lambda F, doesn't matter. So universal equation for all waves. And I know lambda, that's this. I know V sub W, that's this. I need to find F, as simple as F is V sub W divided by lambda. Okay. Doesn't get easier than this. So it's 2.00 meters per second divided by 0. Again, get this 5 centimeters into meters, 0.0500 meters. You find out that the frequency is going to be 40 hertz. What that means is that if you every second, if you watch how many of these little ripples go by you, 40 of those cycles will go by you in just a second. 40 hertz, it means 40 of these waves per second. Okay, moving on. Open stack, 16.51. It says scouts at a camp. Shake the rope bridge. They have just crossed. And observe the wave crest to be 8.00 meters apart. If they shake the bridge twice per second, they're causing a disturbance. What is the propagation speed of the waves? All right. So what do we know? Well, we know if I just do it right here, it's pretty small. We know the wavelength because we know that the wave crests are 8 meters apart. That means lambda is 8.00 meters. Again, scouts at a camp shake the rope bridge. They've just crossed and observed the wave crest to be 8.00 meters apart. That's lambda. If they shake the bridge twice per second, that's a frequency. What is the propagation speed of the waves? Well, if I shake it twice per second, 2 shakes, that's 2 hertz. F is 2 hertz. All right, and so simply enough, V sub W, I use the universal equation for waves. V sub W is lambda F. So it's as simple as 8.00 meters times 2 hertz. 8 times 2 is 16. 16.0 meters per second. There you go. Pretty much 2 lines. All right, so that gets the basics of waves going. All right, so next thing, waves have some interesting properties of their own. One of them is called superposition, which is a good part of what chapter 17 is about. They decided that we're going to talk a lot about superposition, but again, that's something that waves do. So let me go to the textbook real quick, and let me discuss. I think it's best to discuss with the picture what I'm talking about. So I'm going to go to the textbook. One second. All right, so hang on, let me share my screen. I found what I want. All right, share my screen. Okay, so in discussing superposition, waves can, when waves pass through each other, they can actually pass through each other like a couple of ghosts. When they pass through each other, they affect each other. So in this picture, you see wave 1 and wave 2. They have the same amplitude, as you can see. They're also in phase, all right? They're totally aligned with each other. The crests happen at the same time. The troughs happen at the same time. So you have 2 waves that have the same amplitude. And they don't have to have the same amplitude. They can be different waves. 2 waves. The important thing is that they're in phase. They're experiencing their crests at the same time and their troughs at the same time. When these 2 waves pass through each other, what happens is you create a single wave, and you have what's called constructive interference. Constructive interference means that the wave, the resulting wave, will actually be still in phase with the 2 that are making up the wave, except the amplitudes will be twice as high, twice as great. So you'll see that the waves will constructively interfere with each other. They'll actually make all of their zeros will be at the same location, and all of their any kind of whatever their amplitude is from the origin, whether it's negative or positive, will be enhanced. Will be doubled by the other wave. So the amplitudes will be double. This is called constructive interference. I'll write this on the board in a minute. What happens on the other hand if you have two waves that are 180 degrees out of phase? So an example of this is what I'm about to show you. Here I have two waves. Here again they have the same amplitude. They don't have to have the same amplitude, but in this example they do. And you notice that I call them 180 degrees out of phase. That means that the crest is occurring, or the crest of one wave is occurring at the trough of the other. Okay, so they're half a wavelength out of phase. So the crest of one, occurs at the troughs of two, and the crests of two occur at the troughs of one. So they're so when that happens, what happens is that we refer to this as destructive interference. The two waves literally, in this particular case, where they have the same amplitude and they are 180 degrees out of phase or exactly out of phase, or where as I said, the crest of one is at the trough, is occurring at the same time as the trough of the other, and the trough of one is occurring at the same time as the crest of the other. Well, what happens there is you have total cancellation. And so the resultant wave is nothing. And so you have what's called total destructive interference there. All right, and so let me go back to the board. I'll write down what I just got done showing. So when I talk about phase, I mean, again, every wave, any given wave is the same except what its phase is. So for instance, if I talk about, let me just before I talk about waves passing through each other, I might talk about a wave that, let's say, looks like this, right? It has an amplitude, capital X, here, negative capital X. And, and I say, okay, well, this is my time axis. Or actually, not my time, my X axis is my Y axis. They're moving in time. Time is what we refer to as a parametric parameter. Now, I want a wave that's 180 degrees out of phase. That means that I want a wave for every single time that a crest occurs for one, it's a trough. So right here, I put a trough. At this point, I put a crest. And here I put a trough every single time, and they're exactly 180 degrees out of phase, as I call it. And I'll explain that in a moment. How would I draw this way? I draw it like, and so it's the same wave, except I basically cut it and pasted it half a wavelength down. That's all this wave is. If I were to basically say move this wave back a half a wavelength, I would be starting, where I'd be starting at exactly what you see drawn here. So basically, a wave, a phase, is nothing more than at what particular location of the waves process are you starting from. So I might say that, so this case, this wave is 180 degrees out of phase or lagged compared to the other wave. They're 180 degrees out of phase. The waves are the same except how I'm looking at them. Basically, this wave is the exact same except I'm copying and moving it back. It's just out of phase by 180 degrees, or out of phase by pi over 2 radians. All right. Now, what we said is that if you take a wave like one and you add it, or they pass through each other, well, what happens is the resulting wave, as I just showed, the resulting wave is actually going to entirely cancel out. I mean, that's it. That's the resulting wave. There's nothing there. I'm basically taking 1 plus 2. Wave 1, wave 2, they totally cancel out because they are exactly 180 degrees out of phase. That was the second example I showed you. This is called destructive interference. waves interfere with one another. Depending upon what their phase is, it can be constructive or destructive, or maybe a combination of both. This is particular an example of destructive interference. One wave is literally 180 degrees out of phase with the other. The first example I showed you is I added, again, these are two waves at this point passing through one another. And when they do this, they destroy one another entirely. And again, the important thing here is that, they have the same amplitudes in this case. If this wave had twice the amplitude, then you'd actually have a wave that was partially destroyed. Okay, now what happens if I instead move this second wave out so that they are totally aligned with each other? All right, so they have 0 degrees, they're totally in phase. So let's get to draw this. Drawing skills are not the best. Okay, so these are two waves that are, again, don't mind my bad drawings. These are two waves that are totally in phase. These waves are totally in phase with each other. So in phase. The result, we would call this an example of constructive interference. The result is going to be a wave that looks pretty much the same, except its amplitudes are going to be twice. So I'll try to draw that. So this guy is twice as high. This one, if I can fit it on here, twice as low, maybe. Lower. Yep, so on there. Twice as high. These amplitudes are twice. All right. Again, that's called constructive interference. And that's exactly if the waves are totally in phase. So again, I'll repeat what I just said. The waves interfere with each other. I showed you the most extreme examples. So two waves of the same amplitude, cap x, that are in phase, perform constructive interference. Creating a wave that is in phase with the constituent waves but have twice the amplitude. All right, that was constructive interference. Two waves of the same amplitude, cap x, what I showed you, that are in phase. That means their crests occur at the same time, the troughs occur at the same time, their zeros occur at the same time. Perform constructive interference, creating a wave that is in phase with the constituent waves, the waves that formed this resulting wave, but have twice the amplitude. And what else did I show you? Two waves of amplitude x, cap x, that are 180 degrees out of phase with each other will perform destructive interference. Effectively canceling each other out. All right, what I showed you is constructive interference and destructive interference. All right, now, in general, though, I mean, I'm showing you, extreme cases, but let me go back to the book. I could have a more general case. A second. So for instance, what happens if I just add two any old waves? So let me go back to so here's a situation where you have wave one. It's a pretty simple wave like I was drawing. The wave two is a wave that has a much smaller amplitude, but a much greater frequency. I add the two together and I get a complicated wave. The resultant wave looks complicated. And yet it's simply formed by two simple sine waves. Okay, so you get this complicated wave from the addition of just two simple sine waves that are different amplitudes, different frequencies. Okay, so in general, you have this great. So one of the things I'll tell you about is that France in the 1800s was very fortunate to have several very high caliber mathematicians, and so I'll mention a number of them, but one of the greatest ones, and we'll talk about this. We talk about this mathematician also, and physics. He's a physicist mathematician, probably the greatest one in the 1800s. Talk about him also in the study of heat transfer. And this particular person is called Jean-Baptiste Fourier. Now, he's a great French mathematician from the 1800s. Mathematician and physicist. So Fourier, that's how you pronounce it. Americans will sometimes call him Fourier, but Fourier is made a lot of great contributions in mathematics and physics. And so one of the contributions, and we hear his name multiple times. One of the contributions was that he showed that any wave that you can draw, any wave that you can give me, is a linear superposition of sine waves. We just got done seeing an example of two sine waves adding up to give something that's complicated, but Fourier proved that, and he can actually show you how he can show you that, how you can do this. He proved that, Fourier showed that any wave was a, a, um, a linear superposition I want to say superposition of sine waves. Of simple sine waves, actually. And so you can take any wave that you like. We'll say any wave, f sub cap n of x, describes any general wave. It is given by a coefficient a sub 0 divided by 2 plus the summation n equals 1 to capital N, and this capital N, the same n here. How many waves am I going to add? Of a sub n, another coefficient, times the sine of 2 pi nx over t plus some phase factor phi. So again, t is the period, and a sub n are coefficients. When I took a class on, the class that's one level above differential equations is called partial differential equations. So actually, differential equations I've been talking about should actually be called ordinary differential equations. The next class up is called partial differential equations. So we really studied Fourier series a lot, and also studied in the graduate level. I studied in upper level electromagnetic theory as well. But I mean, it's very, very interesting how you can literally take any general wave that you can write down, and you can do what's called a Fourier analysis. You can find these coefficients such that you know exactly how to construct it by simple sine waves. So any general wave can be constructed as a superposition of simple sine waves. This is any general wave. A sub 0 over 2, you got to find a sub 0, that's a coefficient, plus adding up. Summation n equals 1 to cap n. That means I'm going to add up n terms. N equals 1, 2, 3, all the way to n. Add up all n of these terms. These are just simple sine waves. Here's the period, and then this is the n. So, for the first term, this would be 1. The second term, 2. Third term, 3, so on and so forth. And then you'd have, this is a big sum of waves, and you'd have to do what's called a Fourier analysis to be able to actually find out what these a sub 0s and a sub n's are. And you have to oftentimes use matrix algebra to do that. Anyway, that is, in the most general sense, what superposition is. I showed you extreme examples of just two waves. One, having the same amplitude. Two waves that are in phase and totally constructively interfere, and two waves that are totally out of phase, 180 degrees out of phase, and totally destructively interfere, and hence cancel each other out. So again, interference. This is interference. This is the interference of multiple waves that combine together form a general wave. So it turns out interference can be constructive or destructive. Okay. All right, so moving on. Now, in some cases, it appears that the waves are moving, but they seem to move, but they just vibrate in place, right? We've heard of these as standing waves. These are waves that seem to move, but they just vibrate in place. a good example of this would be like a guitar string or a violin string. So essentially you have, if you imagine for a moment, you have, let me erase this and give myself more room for drawing some pictures. So, all right, so this is our, I'm gonna erase these words, and I'm gonna redraw my picture. I'm drawing some pictures. So, so again, we're talking about what are called standing waves. Okay, so how do I make standing waves? Well, one thing I can do is like a guitar string or a violin string. I can make sure that the string is indeed fastened to two ends. So if we imagine for a moment that I have two borders here, and I'm going to have a string that's going to be literally tied to each one of these borders. So going across. All right, so what's going to happen here is the wave is, I'm going to tie the string in each place here. String cannot move there. It's tied to the wall. And I'm going to essentially disturb the string. Now disturb it until a point where, you start vibrating the string. You have a vibrating device that starts vibrating the string, and you won't see much of anything. And all of a sudden, and this is really cool, you see this in the lab. It's one unfortunate thing you're not going to see by doing simulations, but you start vibrating the string. There's a little vibrating device. You just pushes, just basically pushes it up and down, up and down, up and down. And you start vibrating the string, and you really don't see much of anything. All of a sudden, out of the blue, you see this beautiful form, come out of nowhere. You'll see this big form. It's like a football. So you'll see, all of a sudden you'll see the string just, you'll see this form come out of nowhere in the string. And this is what we call the first resonance. What's happening is, before this even occurred, you're sending the wave to the wall, it's reflecting off the wall and coming back, and mostly destructively interfering. At some point, you'll send a wave to the wall that actually, when it reflects back, it's actually going to be reflected back in such a way where it totally constructively interferes. So you have a wave hitting the wall, the wave comes back, and at this point we're only talking about one wavelength, or a part of a wavelength. And so the part of the wavelength that comes back is going to partially, more or less, destructively interfere. At some point, you're going to have a wave that comes back that's going to have total constructive interference with itself. Okay, so what you see here is the wave. So the wave totally constructively interferes with itself. This is called a resonance. Same resonance that we talked about in chapter 10. Now, if you were to, what you're seeing here is actually a half of a wavelength. You're seeing, like, imagine if either is your wavelength, you see a zero node, a crest, and back down. So you have to, if you were to continue drawing this out beyond this boundary, you'd have to have this much space to actually complete the wavelength. You don't have that. So what you see here is, you see a node, because this is a node, a node is a a node is a point on the wave, on the standing wave, that does not move. Well, why is that for this? You know, again, this is a wave on a string. So this is a string fastened at two ends. That's what we're looking at. This could be likened to a guitar string or violin string. So like a guitar or violin string. All right. You're seeing a first resonance. Well, you have to have nodes. You have to have nodes where the string is attached to these endpoints or these ends. The string literally cannot move there. It's tied there. So that's why you have to have nodes. Now, what you have in the middle where it blows up is called an antinode. So an antinode, how much space I have? An antinode okay, is used to denote the location of maximum amplitude in standing waves. You're still on here. Of maximum amplitude. In standing waves. So this would be the antinode. Or blow up. So where it gets fat right there is the antinode. So again, the wave totally constructively interferes with itself. This is called a resonance. So again, you start vibrating this wave, and you see nothing. All of a sudden, boom, you see this football shape that comes out. And the two ends where the wave cannot move at all, those are called nodes. There's a node here. And there's a node here. The only two nodes on the string, and this part of maximum amplitude is called the antinode. The antinode is right here. So probably more towards the center. That's the place of maximum amplitude, the antinode. All right. The node is a point in the standing wave that does not move. Again, these two ends cannot move because they're tied to the ends. The string is tied there, cannot move. The antinode is used to note the location of maximum amplitude in the standing wave. Maximum amplitude. That's the antinode. Okay. This is the first form that you will see. Like if you do a waves lab, this would be the first type of a form that you would see. And I'd actually want to make this match what I drew on the other side. Trying to. There you go. Okay, so let's analyze this now. Okay, so we know what a node and we know what an antinode is. All right, so you're going to vibrate it at a certain frequency to make this happen. All right, so we can look at this and say, well, what if we said that the length between these ends, we'll call it L. And what did I just get done saying? Well, the very first wavelength, again, there's this very special wavelength that denotes these situations of resonance. Again, there's all these other wavelengths have been tried, and boom, here you have a particular wavelength that is special, and you see this resonance situation. All right, and so we call this. So this particular wavelength would be equal to. So again, the whole wavelength would be twice the length, twice L. So we would know that L represents lambda 1 divided by 2. The whole wavelength you're seeing here, if allowed to actually fully express itself, would be lambda 1. We'll call it lambda 1. Well, what you're seeing confined in this, maybe the violin or on the violin or guitar, what you're seeing is only half of that wave. So that means that lambda 1 is 2L. Okay, and so the speed of propagation is what? Remember, the speed of propagation is always lambda f. Okay, and so again, we're looking at an F1. So F1 lambda 1 are going to occur together. All right, so F1, you want the frequency, it's going to be V sub W divided by lambda 1. Whatever the speed of propagation is. V sub W is the speed of propagation of the wave. On the string. All right, and I'll show you how to get V sub W in a minute. But assuming that we know how to get, there's a speed of sound, if you will, in the string. So F1 is going to be V sub W, whatever the speed of propagation is, that wave, speed of sound, divided by lambda 1. What is lambda 1? Well, it's 2L. So F1 is V sub W divided by 2L. That is the frequency. That's the first frequency that you would vibrate this wave to see some resonance. This would be the very first resonance that you actually would see. And this first resonance is called the fundamental. This is referred to as your fundamental frequency. Fundamental frequency. All right, and so we would call this also the first harmonic. Okay, kind of talk over speaking music here. All right, fundamental frequency. It's the frequency. I start vibrating this thing at a frequency. I keep increasing the frequency. All of a sudden, boom! I find the right frequency to generate this first resonance. Now, there's other ways that I can get resonances, and so what I would do in the lab is I would continue vibrating the frequency, and I would then, if I continue increasing the frequency, this waveform will go away. You'll start seeing nothing again. You keep increasing the frequency, and all of a sudden, I will pop up another waveform. So again, this is the fundamental. Let me look at the next waveform. So how would I figure this out? Well, I would go back and I use the same picture as above, and I figure out how do I fit the next wave in here. And this between these two ends. And these ends are still of length L apart. Well, what I can do is I have to have nodes where the string is tied. Well, the next place I can have a node is in the center. So I can actually draw something like this. So I have a node in the middle. So now I have a situation where, yeah, I have the nodes at the ends like I'm required to, but now I have a situation where I will see a wave come up that looks like this, and this will be the second harmonic. All right. And so how do you figure that one out? Well, again, I told you before that the fundamental frequency F1 is the speed of sound, or the speed of sound of the wave divided by 2L. Well, how do I figure this one out? Well, I know again that, let's see, lambda 2 now, it's the next wavelength that I'm considering. Well, let's see here. I actually get a full wavelength confined in this length. So lambda 2 actually is L. So I know that F2 would be V sub W, same speed of sound, divided by lambda. Well, in this case, lambda is not 2L, lambda is just L. So my F2 would be V sub W over L. That is my first harmonic, or sorry, second harmonic, my first overtone, also known as the second harmonic. This was the fundamental frequency. Also known as the first harmonic. Okay, different ways of saying the same thing. I can continue on, all right? Continue vibrating the waves. This form goes away, and I continue increasing the frequency, and I get another picture. Still the same structure. The ends are the length L from each other. And now how can I do this? Well, I have to have nodes on the end. I can stick nodes through the center. 2 of them in the middle. So what I can get now is so that's a wavelength and a half. All right. So if I take a look at what is lambda, well, again, lambda 3. Well, I have, this is one wavelength, just like before, the 2 humps, the 2 loops, as it's called. Then I have another half. So lambda, so basically L is equivalent to 3 halves lambda 3, 3 halves of them. Not, a little bit, basically a wavelength and a half. And if I were to say, oh, well, F3 is V sub W over lambda 3. All right, if I say that, well, then what is lambda 3? Well, lambda 3 is 2/3 L. I mean, basically multiply both sides by 2/3. All right, and so I would get that if I divide it by 2/3, I get 3 halves. And so I find out that lambda 3 or F3 is V sub W, actually 3 V sub W over 2L. And I can keep playing this game on and on and on, right? And I would find out that in general, I could say that, so in general, let's look, see if we can find a pattern. I have 1 over 2L, 2 over 2L, 3 over 2L. All right. So my pattern is very much, I'm going to kind of erase stuff here for real estate. Now, my pattern is, if I were to look at the nth frequency, again, that was the nth frequency, so f sub n, the nth frequency would be some n v sub w over 2L. Again, this is wave on string. All right, n equals 1. We refer to that as the fundamental frequency. Or first harmonic. N equals 2. We call that the first overtone. Or the second harmonic. N equals 3. That's the second overtone. Don't get these terms mixed up. I sometimes do myself. Or the third harmonic. So on and so forth. You can keep doing this. And you can figure out that, well, I have a generalized formula. Whatever I put n in, n is 1, I get the fundamental. N equals 2, I get the first overtone. N equals 3, the second overtone, and so on and so forth. And I can develop these waves, and I can continue drawing those pictures all day. All right. So again, now one of the things that you might ask is, how do I figure out v sub w? So that's provided I know the speed of sound in a wave on a string, but what determines that? All right, so let's find out what is v sub w. So again, v sub w is a propagation speed. Of wave on a string. All right. Turns out that propagation speed is determined by two things. Turns out that v sub w is equal to the square root of tau over mu. All right. And so tau is the tension in the string. And mu is the linear mass density of the string. Basically in kilograms per meter. You take a string, you put it on a mass meter, just coil it up, stick it on a mass meter, and figure out what its mass is, and then figure out its length. The mass divided by length, that's just how much mass per length. You take a string, coil it up, stick it on the mass meter, you'll get a reading. That's so many grams probably. And then you figure out how long that string is. You measure that. That mass divided by that length is your linear mass density. Very simple. Now, so one of the things you might notice if you're going to, let's say, a violin recital, you might notice that, my daughter played violin for a while, and the first thing a teacher does is she takes the instrument and she tries to tune it by tightening it. And what is she doing? Well, she's increasing the tension to increase v sub w, or reducing the tension one way or the other, to change v sub w. When you change v sub w, you've changed f sub n. So your violin, for instance, there's a way of playing, let's say, the note C. So assuming that the piano in her house plays the note C correctly, what she's trying to do is she's trying to listen. I'll talk about what she's actually listening for in a minute, in the next topic. But she's trying to listen for what's called beats. And she wants these beats to go away. And so how that happens is she wants to change the frequency that your violin is playing, that your violin's version of C is playing such that it matches the C from the piano. And so how do you do that? Well, you increase or reduce the tension, which changes the propagation speed on the string. And oh, by the way, that's directly proportional to the frequency. So you want to get your violin's frequency to be that of the middle C, let's say on a piano. So you notice that your teacher's tightening or reducing the tightness of the strings. Well, that's what he or she is doing. Okay. Now, that gets us into the next topic. I kind of alluded to it, is what is that violin teacher listening for? All right. And so next topic is going to be called beats. All right. So I'm going to erase this. Talk about standing waves. Talk about beats. Okay. So beats is a phenomena. It's a phenomena that two waves so it's the interference, what you hear. So you hear, beats are observed when two waves of similar but different, but slightly different frequencies. Well, I'll say two waves of slightly different frequencies interfere. So, for instance, if you strike two adjacent keys on the piano, so if you strike two adjacent keys on a piano, you might hear an unpleasant and slow warbling sound, if you will. You might, try to take two keys that are very similar in frequency, and you might hear between them, you might hear a little slow or like warbling sound. That you might find to be unpleasant. Or let's say you're, between two jet engines on an airplane, you might be, you might relaxing. The jet engines might have similar frequency, but they may slowly interfere with each other. And so, what causes this to happen? So again, you have two waves that are similar in frequency, but they're different. They're different, and they're going to create this extra warbling sound, which we call beats. All right. So this warbling sound we refer to as beats. This warbling sound, if you will, is what we call beats. Okay. Let's see mathematically how beats work. Let's imagine adding two very similar waves. All right. We'll say I'm going to add x equals, I'm going to take a wave, I'm going to sum of cap x cosine of omega 1t plus cap x cosine of omega 2t. I'm taking a situation where the amplitudes of both the waves are the same. Omega 1 is So omega 1 is a few hertz different, or I say a few, I guess it's radians per second, different than omega 2. They're not that different apart, they're just slightly different. Okay, I'm going to add these two. Well, what do you do? Well, first thing I'm going to do is I'll factor out cap x, and just do a little algebra here. So x will be cap x, and then I factored out, I get sum of two cosines. Cosine of omega 1t plus cosine of omega 2t. Nothing too complicated yet. I'm going to employ a trigonometric identity. So again, you can look this up, or so recall a trigonometric identity. That is, if I just take two general variables, cosine theta plus cosine of phi, and I'm adding two different variables, angles, or what do you want to do? Well, if you add them up, that's the same thing as if I took 2 times the cosine of the sum of theta plus phi divided by 2, multiplied by the difference. Cosine of theta minus phi over 2. Okay, so I'm taking addition and I change it for a multiplication. Then cosine theta plus cosine phi is 2 cosine of theta plus phi all over 2. Again, all of this is in the argument of the cosine function, times cosine of theta minus phi all over 2. Again, this theta minus phi, this fraction is entirely within the cosine function. I'm going to utilize that. You can look at this trigonometric identity. There's a, and I think it's called a sum identity or something like that. But you can look it up quite easily. And so what I'm going to do is I'm going to employ this relationship here. All right. So let's I'm going to erase these top words here for real estate purposes. So I have these two things I want to add. I want to utilize this relationship. So how do I do that? Well, so what I'm going to do is I'm going to say that x. Okay, so I have to have an extra 2 out front. So I'll put that out there. So it's 2 cap x cosine. Okay. Let's see here. My theta is omega 1t, and my phi is omega 2t. So theta plus phi is going to be omega 1t plus omega 2t, or factoring it out. I'll do the difference. I'll do the difference one first. Again, that's omega 1t minus omega 2t times 2 divided by 2. So I'll have basically, I'm just factoring it out. Omega 1 minus omega 2 times t divided by 2. I'm just writing the second factor first. No big deal. And again, theta plus phi is omega 1t plus, theta minus phi, apologize, is omega 1t minus omega 2. I just factored out the t. So again, I'm writing the second factor first. Okay. So I could have written it like this, I suppose. To allay confusion, let me just do that. Turns out to be the same thing. Normally in the trigonometry books, you'll see it written the other way, but again, it doesn't really matter. All right, so we can do that. So again, my theta is omega 1t. My phi is omega 2t. Omega 1t minus omega 2t is what I have on top. I just factor out the t. And then I have cosine of omega 1 plus omega 2 t divided by 2. All right. So I'm utilizing a trigonometric identity right off the bat. Now I'm going to employ the relationship between regular frequency and angular frequency. Remember that in general, omega is 2 pi f. We learned that back in chapter 10. So we could say that omega 1 is 2 pi f1, omega 2 is 2 pi f2, right? So I can stick the 2 pi's in there. I can pull out the 2 pi's. They're common. So I can write that little x is 2 cap x, and now I have cosine of what? Well, I put 2 pi f1 minus 2 pi f2. I can pull the 2 pi's out. I have 2 pi f1 minus f2, all divided by 2 times t. I'm getting the ordinary frequencies in hertz, like you normally would work in. And then, of course, same deal over here, times cosine of 2 pi f1 plus f2 times t, all divided by 2. All right, so now I'm going to redefine a few things. I'm going to define what's called the beat frequency. All right, so beat frequency, I'll call it f sub b, is simply going to be the absolute value of f1 minus f2. Difference of the two beats. I put absolute value in case, it doesn't really matter what you call F1 or F2. And remember, the cosine function is an even function anyway. So remember, cosine is an even function. Cosine of negative theta is the same as the cosine of theta. It's an even function, so it doesn't really matter. I put the absolute value to be general, right? All right, so and then we call this the beat frequency. And then we can define what's called an average frequency. The average is nothing more than adding the 2 and dividing by 2, right? I have two things, I add them up, divide by 2, so F average. It's nothing more than adding up the 2 frequencies and dividing by 2. If I want the average test score, I'd add up 20 test scores divided by, I'd add up all 20 test scores divided by 20, right? So again, that's just an average. I'm going to employ that nomenclature here. So I'm going to erase the top equation. And so what you get now in this derivation is x, 2 waves together, 2 cap x, 2 times the these 2's, I'll basically cancel them out. So I'll cancel out these 2's. And what I get is cosine of pi times beat frequency times time times the cosine of, and then f1 plus f2 over 2, that's the average. So it'll be the cosine of 2 f average times t, or 2 pi f average, I'm sorry. Two pi f average times t. Okay, so that's what I get down to. I effectively have 2 cosines multiplying each other. One that has, I'm assuming that F1, F2 are not too different from each other. So this is going to be a very slow frequency, if you will. I mean, very slow, very low frequency. And then I have the other one that's basically about the average frequency. So you'll generally will hear, if I take 2 tones, and play them together, you'll hear the average of the two tones, but superimposed on top of that will be a slow warbling caused by the beat frequency. All right, so again, this will be the equation for it. So I'm going to play a little sound bite to demonstrate this to you. One second. A little sound bite got off of YouTube. All right. So tuning forks. Tuning forks, when you strike the tuning fork, we have plenty of tuning forks in the lab. When you strike the tuning forks, they will play a certain pitch. They'll play a sound of a certain frequency. All right, so listen carefully. (250 hertz, 238. So they're only 12 hertz apart. You hear the slow warbling, that's the difference between the two. So you hear an overall average frequency and a slow warbling of the beat frequency superimposing. All right, so that's what you just heard. When you heard the two tuning forks played together, you heard an overall background of the F average. So that would be what 238. See, that'd be 244 hertz, the average of the two, but a beat frequency superimposed with 12. Now your ear can perceive a 12 hertz frequency very easily. Something like 244 hertz is going to be something that's going to be very hard for your ear to actually perceive any more than just a tone. But your ear can hear the warbling of a 12 hertz frequency very easily. All right, so that's what you're hearing. That warbling sound, that was the beat frequency. That was 12 hertz. And then the other multiplier you heard, you heard not the frequency of any one of the tuning forks, but their average. Okay. So let's work. Let's see. I think it's time for some problems. Yeah. Let's work some problems. I'm going to look at OpenStax 16.57. All right, so that says a car has two horns. One emitting a frequency of 199 hertz. And the other emitting a frequency of 203 hertz. Okay. What beat frequency do they produce? So what was our formula for beat frequency? Well, we know that F1 is 199 hertz. F2 is 203 hertz. Beat frequency, the absolute value of F1 minus F2, or the absolute value of 199 hertz minus 203 hertz. The beat frequency will be 4 hertz. That's it, 4 hertz. So these two horns, you heard that warbling, real slow warbling of just 4 hertz. What we heard in the demonstration was 12 hertz. Okay. Do another problem. OpenStack 16.59. Two tuning forks, just like we saw. One having frequencies of 460 and 464 hertz are struck simultaneously, just like what we just saw, but different frequencies. What average frequency will you hear? Frequency will you hear? And what will be the beat frequency? Or what will the beat frequency be? All right, two tuning forks, just like we saw in that example, that demonstration, having frequencies of 460 and 464 hertz are struck simultaneously. What average frequency will you hear, and what will be the beat frequency? Well, the average frequency will simply be F1 plus F2 all divided by 2. F average, I can do this right now in my head, but we'll just do it officially. 460 plus 464 divided by 2, that comes out to be 462 hertz. Okay, so that's your average. Your beat frequency will be the absolute value of F1 minus F2, or your beat frequency will be the absolute value of 460 minus 464 hertz. Beat frequency will be 4 hertz. Sorry for the moving all over the place on my whiteboard here, but all right. So again, all I did was took the two frequencies, add them together, divided by 2. That got me the average, 462 hertz average. Beat frequency is nothing more than the absolute value of F1 minus F2, which will be 4. Absolute value of 460 minus 464 is just 4. Okay, so now so we'll move on to the next concept. And that is that waves carry energy. All right, so I'm going to talk briefly about this. It's going to be very important when we talk about sound waves, and it'll be very important when we talk about electromagnetic waves. But let's kind of introduce it. So energy and waves, and then intensity. All right, that's what I'm going to talk about now. So waves carry energy. A little smaller on the camera. All right, there we are. Energy, waves, and intensity. So waves carry energy. Talking about periodic motion. Let's make an analogy. With oscillations. Recall in oscillations, I said the work was what? 1/2 kx squared, right? Well, if I remember that x of t back in oscillations was what? Cap x cosine of omega t. All right, again, going back to oscillations, draw an analogy, and then I'll just make the analogy to waves. All right. So in that case, well, what do I put in here? Well, I find out that I'd have 1/2 k. I'm going to square this x. This x goes in here and substitute. So cap x squared cosine squared of omega t. All right. And so what we see here is that the energy for an oscillatory or for a system that's periodic is going to go like the amplitude squared. So going back to waves, again, this is a weak derivation, but again, anything more advanced would be too much advanced math. So the energy in waves goes like, so I always put this proportional to, looks like an alpha the way I draw it, proportional to amplitude squared. That's the thing to take away here. The energy in a wave is proportional to the amplitude squared. Okay, whatever the amplitude is proportional to the amplitude squared. This is just an analogy to kind of develop why this would be, let's say, in oscillations. Oscillations, I'd write something like this. Okay, now we develop, so now we understand that waves, energy in a wave is proportional to its amplitude squared. Let's develop a concept called intensity. Given that the waves have energy, they're going to have a power. Remember what power is. Power is energy, or it's officially work over time. Change in work with respect to time. So energy over time, you know, its units are joules per second, which we call a watt. All right, so again, anything that has energy delivered per unit time is going to have a certain power. The intensity, which I call I, is simply going to be the power divided by the area receiving that power. So it's a power divided by the receiving area, or simply power divided by area. That's the definition of intensity. Okay, so it would be in units of watts per meter squared. Okay, that'd be the units of intensity. We'll talk more about that in other contexts. I'm just giving you the definition. All right, so now let's work a couple of problems to kind of get this out, and then let's go on to sound. Speaking of sound, we got a little thunderstorm coming right now. All right, OpenStax 16.63. That says ultrasound of intensity (1.50 times 10 to the second watts per meter squared) is produced by the rectangular head of a medical imaging device. Okay, measuring .00 by 5.00 centimeters. What is its power output? All right, so the problem reads, ultrasound of intensity 1.50 times 10 to the second watts per meter squared is produced by the rectangular head of a medical imaging device measuring 3.00 by 5.00 centimeters. What is its power output? All right, and let me give you a moment here. I'll erase the board. Okay, so I'm told the intensity, I is 1.50 times 10 to the second watts per meter squared. Hold that. I got to find the area. Okay, this area is going to go through. This power is going to go through a certain area. Well, the area is a rectangle, right? Area of rectangle is length times width, right? So I got to put it in terms of meters. So it was given to me in centimeters. So it's going to be 0.0300 meters times 0.0500 meters. If you work that out, you get 1.50 times 10 to the negative 3 meters squared. All right, there you go. And my definition of intensity is power over area, and I want power, so I cross multiply. Power is simply intensity times the area. So simple as that. I get 1.50 times 10 to the second watts per meter squared times 1.50 times 10 to the negative 3 meters squared. Meter squareds cancel. Power I will find is 0.225 watts. That's the power of this ultrasound device. Okay, another problem. OpenStax 16.65. All right, what's that? To increase intensity of a wave. By a factor of 50. By what factor should the amplitude be? Okay, so to increase the intensity of a wave by a factor of 50, by what factor should the amplitude be increased? All right, so start off by saying, well, we have some intensity I1, and I said that's proportional to some amplitude cap x1 squared. We could also write that the intensity after, I want to talk about a higher intensity. So I'll say, well, I2, whatever that intensity is, it would have to be proportional to some amplitude x2 squared. Yeah, these are just, my initial intensity, and then I want to increase it by, say, a factor of 50. I get the relationship there of a new amplitude corresponding to that. Well, what I'm being told here is that I2 is 50 I1. I want to actually increase the intensity, my new intensity by a higher one. So what do? Well, I would then say, well, okay, well, I2 is proportional to cap x2 squared. Well, I'll stick 50 I1 in here. So 50 I1, okay, is proportional to cap x2 squared by a simple substitution. All right, so again, I know that I2 must be 50 I1, so instead of I2 proportional to cap x2 squared, let's make it 50 I1 proportional to cap x2 squared. And by the way, I1 is what? I1 is proportional to cap x1 squared. So instead of writing I1, I can just write cap x1 squared there. So this becomes 50 cap x1 squared proportional to cap x2 squared. Instead of writing I1, I'll just write down, 50 cap x1 squared. And then I can then say, well, cap x2, and take the square root of each side, should be proportional to the square root of 50 times cap x1, or cap x2 should be proportional to about 7.07 cap x1. So if I want to increase the intensity by a factor of 50, the amplitude has to be increased by a little bit more than 7. By a factor a little bit more than 7. Okay? Now I want to focus on sound. I've been talking about waves in a string. I'm talking about more mechanical waves. Let's now talk about sound waves. All right. I'm going to erase this now. So sound, okay, sound is defined to be a disturbance of matter. That is transmitted from its source outward. All right. So sound is a periodic wave. Sound is in the form of a periodic longitudinal wave. Okay, that is the form of sound. Hearing is the perception of sound. Just as vision is the perception of visible light. Anybody out there wants to be an audiologist? Well, hearing is the ability for, say, a human being or an animal to perceive sound, just as vision is the ability to perceive light or visible light. All right, so we use these terms. Let's make sure we know what they mean. Okay. Defining things here. So, so sound, like all waves, travel at a certain speed. And has properties of frequency and wavelength. Okay, and so essentially you can observe direct evidence of sound compared with light a couple of different ways. For instance, you can watch a fireworks show. And see the explosion before you hear it. So I once lived in downtown St. Louis, Missouri. I went to Washington University in St. Louis, and my first job was in St. Louis. And I lived near Busch Stadium, where the St. Louis Cardinals play. And they were actually in some sort of a championship game around the time I lived there. You know, they're a pretty good baseball team. And they were in a championship game, and they had won. They'd beaten the Braves, I believe, or somebody. And so it's interesting is I was watching on television. I wasn't actually at the stadium, but I lived right near Busch Stadium. But I was watching the game, and I would see the fireworks, you know, on television. Boom! You see the fireworks on television. So all of that information would be transmitted to me via the speed of light. And then I would hear that sound of fireworks about a second or so later in reality. You know, I'm seeing on television, I'm getting at the speed of light, and then lagging behind because of the speed of sound was the actual sound of the explosion reaching me, because I lived, you know, near the stadium. So it's interesting, you know, I was kind of thinking about that, you know, I was watching the game, you know, I was thinking about exactly this. Another example is you hear the thunder outside, is you can actually figure out how far a lightning strike is. So there's a nice little formula you can use to calculate how far away how far away the actual lightning was. So for instance, you can figure out how far away a lightning bolt is from a thunderstorm. But essentially, what you do is you look at the flash of lightning, and you figure out. So you time the distance. I'm sorry. You time the duration between the lightning flash and the thunder clap. And you divide by 5. When you do this, you find out how many miles away the lightning is. So this gives you how many miles away the lightning is, or lightning was. Because the speed of sound is much, much, much less than the speed of light. All right, so the rule of thumb is see the lightning flash, wait for the thunderclap that corresponds to it. That amount of time, divide by 5. You get roughly about how many miles away that lightning was. All right. Another thing, as I said, with sound waves, like all waves, they obey that basic equation I told you about. Okay, so now, another thing. You can directly sense pitch, or you can directly sense frequency. Which we call pitch. So you can hear a high-pitched noise versus a low-pitched noise. We can directly sense that. We cannot the wavelength, though, cannot be directly sensed directly. You can only indirectly sense it via the size of musical instruments. So like, for instance, like in the violin family here, you have high pitch, small wavelength. You'd have the violin, and you have various, I think you have cellos and other stuff, but you have at the very end, you have low pitch, large wavelength, you have the big bass. So it basically looks like violin, except it's just much, much bigger, right? And so you can see there, you can see the fact that there's a, so we understand why this relationship is true, because we know that B sub W is lambda F. So in the case of a high pitch, let's say we have high pitch. That means, it's in the case of the violin, it means that F is big, F is large. That means you have to have a smaller lambda because the speed of sound is what it is. You have a speed of sound, that's on a particular string of a certain tension and a certain mass density. Speed of sound. So you're going to have the same speed of sound for each instrument. However, for higher pitch, you must have a smaller lambda. Hence the sound box. Essentially what you actually hear is you actually don't necessarily hear the vibrating string. The vibrating string will vibrate the sound box. The sound box is what you actually hear. So the sound box of the violin is what you hear, and so you have a larger, higher pitch corresponds to smaller wavelength. Big number multiplied by a smaller number. Here for the bass, you reduce the wavelength. You reduce the frequency because it's a lower pitch. So in so doing, you have to make up for that by increasing the wavelength. So these two numbers multiply together. If one number is smaller, the other number has to be bigger, vice versa. So for instance, in the case of the violin, you have a larger number for F, higher pitch. You have to correspond with a smaller number for lambda, smaller size, smaller wavelength. For the bass, lower number for F, lower pitch, bass is a deeper sound, corresponds to a larger number for lambda. So you get a bigger sounding box. Again, this equation applies for all waves, including sound waves. B sub W is lambda F. It applies for all waves. Okay. Now, the speed of sound is material dependent. Okay. So the speed of sound depends on the material through which the sound waves propagate. Take a look at the material and read the speed of sound. So, for instance, you might ask, well, what determines the speed of sound? Well, remember, I'm going to kind of make an analogy back from strings. It was something like tau divided by mu, right? Square root of tau over mu was what it was for strings. This is like rigidity divided by density. All right, you can put a square root on there if you like, but again, you look at materials that are more rigid, like liquids are more rigid than gases. So liquids would have a higher rigidity than gases, and solids are more rigid than liquids. So the rigidity increases. Density, the lower the density, essentially you don't have as essentially it's inversely proportional to propagation. It's kind of it's like this. It's kind of like that well, gases are going to have least density, and then liquids and solids will have a higher density. So you have rigidity divided by density is really roughly what determines the speed of sound. Okay, And so you'll notice that the speed of sound is, you can look it up for various materials. I will give you a table to kind of give you an idea, and we'll kind of look at the table and talk about different speeds of sound. Again, speed of sound is material dependent. So just kind of give me a moment here. I'm going to bring up the corresponding table for that. Give me a second here. Here we go. All right. Share my screen. Okay. All right. So what you see here in your table, your book should have a similar table. You'll notice that this is from OpenStax. The speed of sounds in various media. All right. So now you notice that, you know, for liquids and gases, and I'll explain this in a moment. Liquids and gases together are called fluids. For fluids, there's a temperature dependence as well. So you're seeing gases at 0 degrees Celsius, for instance. And you notice that, you know, you have speeds of sound for various gases. Speed of sound in air at 0 degrees Celsius, well, I'll talk more about this in a moment, is 331 meters per second. Yeah, let's say you have it's all entirely carbon dioxide or oxygen instead. The speed of sound is different. Liquids, you'll notice why, because they're more rigid. They'll actually have a speed of sound that is higher than any of the gases. So you notice that there's, you know, you see the speed of sound of various liquids: ethanol, mercury, fresh water, salt water, so on and so forth. Then you get the solids. Solids, the speed of sound seems to even be greater. So you imagine, you know, if you clack two things together underwater in a swimming pool, the sound waves go very, very fast compared with the same kind of clacking of two, like say, two metal objects together outside. So again, the speed of sound depends on the medium through which the sound waves are passing. All right, and so you could look this up. You have a table in your book to look this up as well. It would be in chapters 16 or 17. I didn't bring my book with me, but again, there is a table, you know, that gives you speed of sound in your book. All right, I'm going to stop sharing. So you look up the speed of sound. That speed of sound is your B sub W. So again, you know, the speed of sound that you saw on the table. So the speed of sound in the lookup table is V sub W. That's the V sub W that you use in your calculations. So you literally can look it up. Now, I mentioned that there was a temperature dependence of on some of the fluids. So let's look at the one for air. We're most interested in talking about sound in air. So let's kind of write down what the equation would be to figure out the speed of sound as a function of temperature. So V sub W, speed of sound in air, is given by V sub W is 331 meters per second times the square root of T over 273 Kelvin. Okay, that is how you find the speed of sound in air for it. And then T is temperature in Kelvin. So recall, that temperature of Celsius is what, Celsius temperature was everybody in the world uses except for us. Celsius temperature is a nice power 10 temperature scale. It is a decimal, or I would say a power of 10 temperature scale. Based on the freezing point, and boiling point of fresh water. And so we assign nice numbers to these. For instance, we say, 0 degrees Celsius corresponds to boiling or freezing. Right? And 100 degrees Celsius corresponds to boiling. Again, very nice powers of 10 type numbers, a 0 to 100 system based upon one of the most important substances to humanity, water. Right? So I don't know why we use a crazy Fahrenheit scale. I won't get on that. But but again, this is before we understood atoms. We didn't understand atoms. People who formulated this temperature scale based it upon something that was very important to us, we humans, and that is water. We drink it, we bathe in it. Water is very essential to our lives. All right. Now, as we got smarter, we got to understand atoms. And we realized that the temperature is really, and again, I talk about this in my thermodynamics my thermal physics sections. But temperature is really a measure of the average thermal energy. So the temperature, what is it? Temperature is a measure of the average thermal energy. Is a fancy word for kinetic energy. Let's say atoms or thermal energy. Well, we'll talk about that. And the constituents of the material. I.e., the atoms or molecules that make up the material. And I prove this in my thermal lectures. But temperature is a measure of the average thermal energy. So you increase the temperature, you increase the average thermal energy of the atoms, molecules of your system. Well, if you reduce the temperature, you reduce the thermal energy. And so imagine if you reduce the temperature so much that you reduce the thermal energy to the point where things stop moving. That is called the absolute zero. The Kelvin temperature scale is based on absolute zero. That's the lowest temperature you can achieve. All right, and so Kelvin temperature scale says that 0 Kelvin is absolute zero. And essentially, if you want temperature Kelvin, it's let's see, temperature Kelvin is temperature Celsius plus 273. Yeah, so 0 Celsius gives me 273 Kelvin, right? 100 degrees Celsius is 373 Kelvin. So that's the way to get it. So the freezing point in degrees Celsius is 0 degrees Celsius. That corresponds to 273 Kelvin. And the boiling point of water is 100 degrees Celsius. 100 plus 273, that's 373 Kelvin. So it actually is the same scale as the Celsius scale, except it's offset by 273. And so that's why you see that 273. So if you were to say, oh, you're saying that, that if you remember reading that table said, oh, well, this for air at 0 degrees Celsius, we saw that the speed of sound was 331 meters per second. Well, yeah, if I put 330, but if I say, oh, 0 degrees Celsius, well, I don't want Celsius, I want Kelvin at 273, put 273 over 273, that's a square root of 1, which is just 1, and I get 331 back. So yeah, but I have to make sure that I use the Kelvin temperature scale. So hopefully you come to this class with knowledge of the Kelvin temperature scale somewhat, and the Celsius temperature scale. But again, if I know my temperature in degrees Celsius, I can simply add 273 and get the temperature in Kelvin. I have to use Kelvin temperatures to use the speed of sound formula. Okay, so speed of sound in any materials, well, at least liquids and gases and liquids, which are called fluids. Speed of sound in any material in any fluid is temperature dependent. So you have to specify the temperature in which the speed of sound is being taken. So for air, we have a nice formula. We can adjust the speed of sound based upon temperature. Okay, so the speed of sound is nearly independent of frequency. Means there is no dependence of frequency on the speed of sound. It doesn't matter what the frequency is. Essentially, if this were not so, then one would hear the high pitch instruments before the low pitch instruments in a marching band. So speed of sound is independent of frequency. All right, so let's do a few problems to kind of get these ideas hammered out. I'm looking at OpenStack 17.1. That says, when poked by a spear, I didn't make these problems up. An operatic soprano. lets out a 1200 hertz shriek. What is the wavelength? I mean, what is its wavelength? If the speed of sound is 345 meters per second. All right. So when poked by a spear, an operatic soprano lets out a 1200 hertz shriek. What is this wavelength at the speed of sound is wavelength if the speed of sound it is 345 meters per second. All right, so again, we're going to go back to the basic equation. True for all waves, V sub W is lambda times F. And I'm being told F, the sound that the soprano made was 1200 hertz. I'm being told the speed of sound on this given day is 345 meters per second. So I said, what do I want? I want the wavelengths. I solve for it. Lambda is simply V sub W divided by F. Or I stick in here 345 meters per second divided by 1200 hertz. And the wavelength of the sound waves will be 0.288 meters. All right, so pretty straightforward problem to get us started here. Okay, another problem. Open stack 17.4. This says, what is the speed of sound? In a medium. Where a 100 kilohertz frequency produces a 5.96 centimeter wavelength. B says which substance in tables in let's see, which substance in open stacks table 17.1 is this likely to be? All right, so what do I know? Well, I know but I don't know, doing part A, I do not know the speed of sound. Looking for that. I do know the frequency. Frequency is 100 kilohertz, or 100 times 10 to the third hertz. What else do I know? I know the wavelength. The wavelength will be 5.96 centimeters, or 5.96 times 10 to the negative 2 meters. Those are all the things I'm just being given. So a simple calculation. V sub W, again, I use this universal formula for waves, lambda F. Lambda 5.96 times 10 negative 2 meters times F, 100 times 10 to the third hertz. V sub W is going to be 5.96 times 10 to the third meters per second. And if I go and look at the table, I found that I look at the table that this speed of sound happens to match that for steel. So likely what the sound waves are going through is steel. And just look, that's a table lookup. Very, very close to the speed of sound of steel. Okay. So next problem, 17.5. OpenStack 17.5. Show that the speed of sound in 20 degrees Celsius air is 343 meters per second. And that's one of those numbers you just kind of remember. 20 degrees Celsius air, typical temperature, comfortable temperature, speed of sounds, 343 meters per second. That's usually what you remember. Let's see if we can verify that. So B sub W is 331 meters per second. We'll use that formula I just gave you. The square root of temperature in kelvins divided by 273. And 273 is in kelvins, of course. That's in the square root. Okay, that's that formula I gave you for, and then again, this is only for air. Don't be using this formula for anything else. It's air. All right. So what's the temperature? 20 degrees. Well, in Kelvin, that's what? Temperature Kelvin is temperature Celsius plus 273. So temperature that I need is going to be the 20 in Celsius plus 273. That's going to be 293 Kelvin. That's what I have to put in that equation. So the speed of sound will be 331 meters per second. That's a square root of 293 Kelvin over 273 Kelvin. And I do all that, I find out verily that I get 343 meters per second. Yep, that's what I said. Speed of sound wasn't 20 degrees Celsius, and I just verified it. Okay. All right, I'm going to do another one here, 17.9. OpenStacks. 17.9. That says if a submarine sonar can measure echo times with a precision of 0.0100 seconds. What is the smallest difference in distances? it can detect. Okay, and then assume that the submarine is in the ocean, not in fresh water. So assume that the submarine is in the ocean, not in fresh water. And it's important for the speed of sound determination. All right, so let's kind of figure out what it is that I'm doing here. So when I make, and this is how radar works as well. If I want to figure out, how far something is away, what do I do? Well, I have like some sort of in this case, a sound, sound device. I send out a pulse. So let's say here's my submarine. And I send out a pulse, basically. So I send out a wave. Let's say I'm trying to detect something out here. Here's my something, all right? Well, the pulse is going to come all the way out. It's going to bounce off whatever it is that I'm looking at, and it's going to come back. And I'm going to receive the pulse. And so if I imagine that this distance here is some delta x, well, what's going to happen is the time that I'm going to measure. So I'm looking for a pulse. The time of return of that pulse is actually going to correspond to back and forth. So going forward and then bouncing all the way back. It's going to be 2 times the distance of where that object actually is. So I'm trying to figure out, if my delta t is the pulse time. Delta t is pulse time. Then delta x is going to then be let's see here, distance is length times time, so 2 distances will be the velocity times the time. Sorry, velocity times the time. So again, d equals vt, but my velocity is the speed of sound, and my delta t is the pulse duration, and that's actually going to account for the pulse going all the way forward, hitting the target that I'm trying to detect, and then receiving that pulse on the way back. So 2 delta x is v/w times delta t. I gotta make sure that factor 2 is important because it's going forward and then back. Okay, I'm sending out the pulse and I'm waiting for it to return. Right, I time that. That time corresponds to going for the pulse going all the way, hitting my target and coming back. Radar works this way as well, except you're not using sound, you're using light. So you bounce off radar off of airplanes or aircraft or something. You're actually using light in this principle, as opposed to sonar, which is sound. Okay, sonar sound, radar light. All right, so I'm going to erase this stuff up here, and I'm going to let's do the problem. Okay, so what do we know? We know the pulse duration. We're told that delta t is 0.0100 seconds. That's the pulse duration. How long it takes me to get my pulse back? What I said, my pulse. I said, how long does it take to get that echo? Basically, this is what's called an echo. So if I yell, let's say I'm in an empty parking lot or something, and there's buildings nearby, and I say, "Hey," and then I hear it coming back to me, "Hey," my voice coming back. Well, that's basically an echo. I sent out a sound pulse. It bounced off of a building, and it came back to me. Right? That's what I heard. This is oftentimes called an echo. So we call this an echo duration. All right. Let's see. V/W. I gotta look this up. It turns out to be 1,540 meters per second from OpenStack's table 17.1, and I use fresh water. I'm sorry, I use salt water, not fresh water. This is what you get for salt water, because ocean water is salt water. Okay, so I have VCW, I have delta T, I'm ready to go. So delta X then is going to be V sub W delta T divided by 2. Okay, solving for delta X, it is going to be 1,540 meters per second times that echo duration, 0.0100 seconds divided by 2, and I come to find that that is going to be delta X is 7.70 meters. So I really only have a device that where I can detect pulse durations as good as 0.0100 seconds. And so the distance, the difference of distances that I can detect is right around the order of 7.7 meters. This gives you an indication of how big are objects you can actually detect. You know, if there's an object that's smaller than this, I mean, I have to have an object about this size to use a sonar device like this. I mean, if an object's smaller, I really can't. It's delta X is too small for me to be able to make that, to actually be able to use that sonar. So essentially, let's kind of remember this. Part B says there's actually a part B to this problem. So 7.7 meters. Let's remember that. So I didn't write it down because it seemed like it was a lot of words. So part B of this problem, I mean, I just did the problem, but part B says, discuss the limits. Okay, this time resolution imposes on the ability of the sonar system to detect the size and shape of objects creating the echo. All right, so kind of just what I said. Basically, this means that the sonar is good for spotting and locating large objects. But it isn't able to resolve smaller objects. Or to detect detailed shapes of objects. right? So the limitation is it really can only detect, kind of tell you, yeah, there's something there, you know, and that's and that's something has to be big, like a ship, all right, or if you're looking for a sunk aircraft or something. All right, let's go to the next topic. So sound waves are pressure waves. Okay, so basically, and we're going to talk about how do you get intensity. The sound waves are pressure waves. And a fluid, a pressure, P is given as a force divided by an area. It's a force over a particular area. And we talk more about this in the fluid mechanics chapter. I'm just kind of saying a little bit about it here, but the fluid mechanics chapter 11, that lecture will have a much more detailed description of pressure. So essentially, it's given in terms of newtons per meters squared, and we honor a special physicist who did a lot of work in fluid mechanics named Pascal. So another great, brilliant French physicist in the 1800s, and typically we'll for short we'll just say PA. So we refer to pressure in terms of pascals. So these are pressure waves. Sound waves are. And so if we want to talk about the intensity of sound wave, you know, generally speaking, intensity of sound wave is power divided by area. But again, power goes like amplitude squared. And so the pressure amplitude, we have a lot of P's here. There's a capital P for power. I'm about to give you a small p for pressure. So we're using P quite a bit. We had little p for momentum earlier. Now we have capital P for power. Now we have little p for pressure. So pressure amplitude, the pressure amplitude of a sound wave we call that delta P, is the it's basically the difference or I say it's half the distance, half the difference of the maximum and minimum pressure in the sound wave. We're not going to really do too much on the pressure amplitude, but again, the pressure varies between a maximum and minimum per cycle. And if you take the max and the min, you take the difference of the two, divide by 2, you get what we call the pressure amplitude. We call that delta P, the pressure amplitude. Okay, and so if you want to figure out the intensity, I'm just going to give you the formula. It depends on this pressure amplitude. Okay, I'm going to erase this. The intensity, given that delta P is an amplitude, power goes to the amplitude squared. It turns out that the intensity for a sound wave is delta P quantity squared, and this is the pressure amplitude quantity squared. This is little p now, divided by 2 rho V sub W. And again, delta P is the pressure amplitude. SI units, I'd be giving that in terms of pascals, newtons per meter squared. Rho, density of material through which sound waves propagate. Okay, that would be given in kilograms per meters cubed. And then V sub W is, of course, the speed of sound. So if I want the intensity of a sound wave, it's the pressure amplitude squared divided by 2 rho V sub W. All right, and so again, that's that intensity would give you watts per meter squared. Okay, so just kind of note that. Now that's sound intensity. You can figure out the sound intensity. So again, what I just gave you is sound intensity. All right, so let's write this one more time. So again, I gave you sound intensity, the intensity of the sound wave. And I'm being very deliberate here for a reason. Intensity is always power, capital P, divided by area. For sound waves, it turns out to be the pressure amplitude, little p, quantity squared, divided by 2 rho V sub W. This is in terms of watts per meter squared. That is the sound wave. That's the intensity of a sound wave. In a medium given by density rho with speed of sound V sub W and pressure amplitude of your sound wave at delta P. Okay, but we also have what's called the sound intensity level. So anybody who's, gone to an audiologist to have their hearing tested, they'll have their hearing tested, and the audiologist is going to give them not sound intensities, but sound intensity levels. You typically will hear, this audiologist will refer to decibels. The sound intensity level is given in terms of what are called decibels. So what is the sound intensity level? Well, it's given by beta in dB. Decibels is typically called dBs. It's given by 10 times the log base 10 of I over I naught. I is the intensity. I naught is 10 to the negative 12 watts per meter squared, is a reference intensity. This is chosen because we humans are so important. The I naught is chosen as is the threshold of human hearing for a person with normal hearing. 10 to the negative 12 watt meters squared. Okay, so now the thing about it is we have a very large range of sounds that we can hear. Okay, so I'm going to bring up a table here. Just, you know, how humans can perceive. We have this tremendous amount of ranges of intensities that we can perceive. So give me a moment. Okay, I'm going to bring up a table. All right, this table is, I think it's table 17.2 in the textbook. Yeah, 17.2. So if you look at the threshold of human hearing, that's considered, you know, 10 to the negative 12, 10 to the negative 12 watts per meter squared. That is, for a person with normal hearing, that is the intensity of sound that person can perceive. If we stuck that into the logarithm, we'd have the logarithm of 10 to the negative 12 divided by 10 to the negative 12, or the logarithm of 1, and that's always 0. And I'll talk more about logarithms in a moment, but the sound intensity level at this point would be 0. And what you see here is that the threshold of human hearing, I mean, humans can hear everything from 10 to the negative 12 all the way to right before your eardrums burst, 10 to the 4th. Okay, that's like 16 orders of magnitude. And that's a challenge in that you want to try to represent, let's say in a single graph, all the sound intensity that a human being can have. And the problem is you're trying to essentially put things together that are in order 10 to the 16 orders of magnitude. That's like everything from, you know, talking about a money, let's say in terms of from a penny all the way to $100 trillion. Okay, I'm trying to put into a graph everything from, you know, any amount of money from 1 penny to $100 trillion. So, you know, you ask yourself, well, what significance is a penny compared with $100 trillion? Well, normally that wouldn't be significant, but the problem is it is significant for hearing perception. Human beings can hear 16 orders of magnitude in hearing. That's like comparing a penny with $100 trillion. Okay, that's the level of hearing diverse sounds that we humans can pick up and perceive. All right, so we need to be able to have a way. So I'm gonna hit stop share here. We need to be able to have a way of representing all of this on a single plot. And so how you do that is you use logarithms. All right, so with a logarithm, you can have something that's 10 to the 16 times, you know, the data can be 10 to 16 times in variation. However, or it can vary everything from 10 to the negative 12 to 10 to the 4th. However, the logarithm is only going to go from negative 12 to 4. So logarithm is the slowest function in the universe. And so again, we need to start reminding ourselves how to use logarithms. All right. So again, so the threshold of human hearing is down here. So if I put I naught over I naught, I get the log base 10 of 1. The log of 1 is always 0. So that gives me beta of 0. We'll talk about this in a little bit here. So let's remind ourselves of logarithms. Right? You might have not seen logarithms for a little bit. Let's remind ourselves of them. We need logarithms to do this work. All right. So again, a logarithm is a way. So you can take data that vary by orders of magnitude. Can be represented together using logarithms. You typically have logarithms at a couple different bases that you're used to. You have the log base 10 of x. Now, log base 10 of x, I could say that's equal to, let's say, a. All right, some number, a. And I want to go from, and I want to figure out, okay, how do I go from, how do I figure out a? Well, again, log base 10, the opposite or the inverse function for that is a power function. If I were to take the power 10 on either side, 10 to the log base 10 of x. Take what you did to the left, you got to do to the right. That's equal to 10 to the a. 10 to the log base 10, that undoes it. The 10 to the power of log base 10 undoes the logarithm, and all you get back is the argument. So here on the left-hand side, I get nothing but x. So x is 10 to the a. All right, so I can figure out x as a function of a by taking the power on both sides. You also, in your calculator, you have the log base e of x, where we refer to this as a natural log of x. E is a very special number in mathematics. And it's an irrational number, so it's like 2.7182, 2.718828. It is it's a very special number in mathematics, and essentially it is the natural base in all of mathematics. And I can explain that later. It's the base of all trigonometric functions. If you try to express a sine and a cosine, you would express it in terms of, you can actually express it in terms of complex exponentials. And I'm not really going to talk too much about that, but again, you're able to do this because of this base e. But anyway, what this means is that you have an e to the x function in your calculator. So you say, oh, I'm going to take e to the natural log of x. Well, let's say this equals, say, some other letter c, some other number c. Well, I take e to the natural log of x. What do I do to the left? I gotta do the right. So I take the same e to the c. E to a power, it undoes the natural logarithm. So I just get x is e to the c. Okay. So in your calculator, you should have something like a e to the x button that does that. And then you should have a natural log, maybe ln x button on your calculator as well. That does natural log function. On your calculator, the one that does the ordinary log, it probably just appears as log. All right, that's all it is. It doesn't say base 10. If you just say log, it's assumed to be log base 10. Okay. So let's talk a little bit more about logarithms. Okay, in case you haven't seen them for a while. You can only do 3 things with logarithms. All right. And so you have 3 special relationships that are true for logarithms. If I take the log of, let's say the log base whatever call it base b. It could be 10, it could be e, it could be whatever. Log base b of x plus the log base b of y. X and y are real numbers. I can write this as the log base b of x times y. So if I take log base b of x plus log base b of y, if I add up two different logarithms, it's the same as log base b of x times y. That's one thing I can do. I also have the log base whatever b of x minus the log base b of y, and that's equal to the log base b of x over y. You get the division there. And if I say that I have the log base b of some x to the a, I can take that power and turn it into a coefficient and bring that a down front. I can say it's the same as a log base b of x. Those are the only three things that I can do with logarithms. That's it. Those are the only three major abilities that I have to use logarithms. Those are the relations. Those are only relations you ever see anywhere. Okay, so let's do some problems to kind of get an idea about this whole news intensity level concept. All right, I think it's best brought out with some problems. So I'm going to look at OpenStack 17.12. Okay, it says, what is the intensity in watts per meter squared of 85.0 decibel sound? Again, oftentimes people call them dBs. Okay, so what do? I know that beta is 85.0 decibels. And decibels, if you're curious, well, let me write the formula down. So beta is 10 log base 10 of I, the intensity, over this reference intensity, I naught. Okay, and so decibel comes from deci, meaning 10. You're multiplying by 10, and you have log base 10, and then Bell from Alexander Graham Bell, the inventor of the telephone. He was actually a brilliant scientist in his own right. He was best known for inventing the telephone, but he is he's somebody who you know, did a lot of research in science, particularly to help deaf people. Okay, so I want to find I. So again, a decibel, if you look at it, I have watts per meter squared or watts per meter squared. That's a unitless number. So really, beta is really unitless. I defined it as an energy level, and hence we call them decibels, right? So there's no real, there's no real unit per se. We have this defined level unit. But I want to try to find I. You know, so essentially, I'm going to write 10 log base 10 of I over I naught. What did I say beta was? 85 decibels. I'll divide both sides by 10. I have the log base 10 of I over I naught equals 8.5. And now what do? Well, I'm going to undo the logarithms. I'm trying to get to I. I is inside that logarithm. So how do you do that? I take 10 to the power of each side. So I'll be very deliberate at first here. So I'll take 10 to the power log base 10 of I over I naught. And what I do to the left, I do to the right. So I over I naught. And I can take 10 to the 8.5. So 10 to the log base 10 of I over I naught is 10 to the 8.5. Okay, 10 to the power of log base 10, that's going to undo, they undo each other. I get the argument back. So the left-hand side simply automatically becomes I over I naught equaling 10 to the 8.5. Multiply both sides by I naught. I get I is I naught times 10 to the 8.5. And I'm ready to plug in some numbers. I is this reference intensity, 10 to the negative 12 watts per meter squared times 10 to the 8.5. I is 3.16 times 10 to the negative 4 watts per meter squared. All right, so what I did is, give me 1 second. What I did was I was given 85 decibels. I went straight to the formula. I just wrote the left side to the right and vice versa. Then I wrote what beta was, 85.0, divided both sides by 10. It got 8.5. I'm trying to get I, so I take the 10 to the power of each side. The 10 to the log base 10 gives me the argument back, I over I naught. What you do to the left, you got to do to the right. So it's 10 to the 8.5. And all that's left is now multiplying, getting I by itself, multiplying by both sides by I naught. We know what I naught is. Right? So that is what that power, so that's I in regular SI units. All right, continue. I'm going to do OpenStax 17.14. That says a sound wave traveling in 20 degrees Celsius air has a pressure amplitude of 0.5 pascals. What is the intensity of the wave? All right, so I'm going to use that formula directly. That's all this problem does. The formula I gave you with the pressure amplitude and the intensity. So speed of sound in 20 degrees Celsius air is 331 meters per second. times the square root of 290 Kelvin over 273 Kelvin, or that's 343 meters per second. I determined that previously. The density of error, and you have to look this up in your book, the density of error is 1.20, at least in OpenStax, kilograms per meters cubed. I need that too. If we're talking about error, that's the medium. Density of error, need to have that. The pressure amplitude is given as 0.5 pascals. And so what I get is I is delta P quantity squared over 2 rho V sub W. Plug it on in. I have 0.5 pascals, quantity squared divided by 2 times 1.20 kilograms per meter cubed, V sub W, 343 meters per second. And I find out that I is equal to 3.04 times 10 to the negative 4 watts per meter squared. That's my answer. Okay. Again, I had to figure out the speed of sound, 20 degrees Celsius air. I had that formula I showed you earlier, 343 meters per second. The density I had to look up, density of air, 1.20 kilograms per meters cubed. Delta P is the pressure amplitude, 0.5 pascals. I have the intensity formula for a sound wave, delta P quantity squared over 2 rho V sub W. Put the numbers in, I get the intensity of 3.04 times 10 to the negative 4 watts per meter squared. Okay. 17.15 is the next problem we want to do. That one says, what intensity level, last time we did intensity, what intensity level does the sound in the preceding problem correspond to? What we just got done doing. All right, so beta is 10 log base 10 of I over I naught. Well, I determined an I in the last problem. I determined an I that was 3.04 times 10 to the negative 4 watts per meter squared. So beta is 10 log base 10 of 3.04 times 10 to the negative 4 watts per meter squared divided by the reference intensity of 10 to the negative 12 watts per meter squared. And that gives me 85.0 decibels. So I go from intensity to intensity level. All right. Do OpenStax 17.18. All right, that says, what is a decibel level of a sound that is twice as intense as a 90 decibel sound? B, what is a decibel level of a sound that is 1/5 as intense as a 90 decibel sound? Okay, so we have what we call decibel math. It turns out that, as I got done saying, that there is, we're talking about sonar systems. You have the concept of sound intensity and sonar systems, and typically you would actually refer to sounds in terms of decibels. Well, radar systems actually are based on a very similar concept, except now you're using electromagnetic waves instead of sound waves. And so the same kind of intensity concept applies. So it turns out that, if you work at a place like Raytheon, like I do, or some areas, in the defense industry, your actual most natural unit to talk about detecting targets, via radar, is you talk about dB, you talk about decibels. So if you're talking about radar systems, all the radar engineers, they'll talk in terms of dBs or decibels. So again, this is one of those things you have to kind of think about. I would refer to it as like decibel math. Decibel math is a little bit different than regular math, and so we're going to see a result here, like in part A, particularly, that's going to be a little strange to you at first. It was a little strange to me when I first did that calculation. All right, and so I wasn't used to decibels before I started working in this industry. So, all right, so let's work the problems out. You'll see what I'm talking about. So the original sound level, intensity level, is beta 1, and we'll say that's 90 decibels. That's the original level. And so I know that beta 1 is going to be 10 log base 10 of some I1 over an I0. So beta 1 corresponds to some I1. And I don't really know what I1 is, and it turns out I'm not going to need to. But, well, we could know, I guess. For instance, given it should be pretty easy because it's 90 decibels. So if I say that 10 log base 10 of I1 over I, now let's kind of practice logarithms, is 90 decibels, right? I'll divide both sides by 10. I get the log base 10 of I1 over I0 is going to be 9. 90 divided by 10 is 9. I take the power of 10 on both sides. I have 10 to the log base 10 of I1 over I0 is 10 to the 9th. What I do to the left, I have to do to the right. Again, 10 to the log percent of I1 over I naught. That just undoes the logarithm. So I get I1 over I naught is 10 to the 9th, or I1, and I can actually solve for, well, I can actually solve for, well, I get the ratio is what I care about, but if I really want I1, I can say that's I naught, or I naught times 10 to the 9th, or I1 would then become 10 to the negative 12 watts per meter squared times 10 to the 9th, or I'd have the I1 would be 10 to the negative 3 watts per meter squared. I mean, if I wanted to do it that way. Again, I'm just doing extra. I do a little extra work to kind of get you more familiar with logarithms. But it turns out that what I can actually do is I don't actually have to do everything I did here. All right, and so I'm going to just kind of make a note of that. I mean, this is kind of for your own edification, but I can actually go back and not do any of this work. I can actually do something that's more clever. I can say, well, I know that beta 1 is some 10 log base 10 of I1 over I naught, which equals 90 decibels. But you want to find out a new I2, right? So you're going to have an I2 that's a 2 I1. You want to double the intensity. So beta 2 would be 10 log base 10 of I2 over I naught, or beta 2 is 10 log base 10 of 2 I1 over I naught, right? Because I2 is just 2 times I1. All right, and so moving on. I can say that I can use one of those formulas for logarithms. So I can say that beta 2 is 10 log base 10 of 2 plus 10 log base 10 of I1 over I naught. I mean, I'm basically taking it apart. Remember, I had the log of A plus the log of B is log of A times B. Here I have a log of two things multiplied together, 2 and I1 over I naught. I can take those apart from that formula. Remember this? Log base, I'll say log base 10 of A plus the log, I think I used X. Plus log base 10 of Y is the log base 10 of XY, right? So I had the XY, the X in this case was 2 and the Y was I1 over I naught. I was able to separate them out. Log base 10 of X, that's just 2. Log base 10 of Y, that's just I1 over I naught. And I have this extra 10 multiplying everything. That's just because that's the way the logarithms are defined. Or sorry, sound intensity levels are defined. All right, so I can do that. Now what do I know? Well, 10 log base 10 of I1 over I naught. 10 log base 10 of I1 over I naught. That's beta 1, isn't it? So beta 1, so beta 2 is 10 log base 10 of 2 plus beta 1. And if you put this in your calculator, you want to figure out what this is. It turns out that the log base 10 of 2 is going to be 10 log base 10 of 2 is 3. So beta 2 is 3.0 dB plus what I have for beta 1, 90.0 dB. So beta 2 is 93.0 decibels. So the strange thing you have to do in decibel language is if you want to double the intensity, You add 3 dB. I mean, it's a strange thing to think about, but that's the way it works out. You want to double the intensity, that corresponds to an intensity level increase of 3.0 dB. So that's one of those things that, you always think of, you always hear people talk about 3 dB, doubling the intensity. Well, 3 dB is what intensity level you need to add to double what the intensity is. Okay. On the other case, I can kind of erase some of this stuff. So I'm going to start here. A lot of this stuff I can kind of reuse. All right, so all I'm asked now is I said, oh, well, now we're being told that I2 is now 1/5 I1. That's what part B is. And so if that's the case, then beta 2 is 10 log base 10, and I2 will be 1/5 I1 over I0. And of course, I can use the same kind of relationship that, this is my X, this is my Y, so I can say this is the beta 2 is 10 log base 10 of 1/5 plus 10 log base 10 of I over I0. Okay, and again, 10 log base 10 of I over I0, that's just beta 1. So I have beta 2 is 10 log base 10 of 1/5 plus beta 1 at 90 degrees, or sorry, 90 decibels. Well, it turns out that this ends up being -7, the first term. So 10 log base 10 of 1/5 is -7.0 dB. Then, of course, you have what beta 1 was, that's 90 dB. And you find out that beta 2 now is 83.0 dB. So taking the intensity down by a factor of 5 essentially means that you're subtracting 7 from the intensity level. Okay. Let me do 17.22. OpenStax 17.22. That says if a large housefly .0 meters away from you makes a noise of 40.0 decibels. What is the noise level of 1,000 flies? At that distance. Assuming interference is negligible effect. Okay. So if a large housefly 3.0 meters away from you makes a noise of 40.0 decibels, what is the noise level of 1,000 flies at that distance? Assuming interference has negligible effect. Okay, so what do? We know the intensity level of one housefly. So one housefly, we'll say, is 10 log base 10 of I over I naught is 40 decibels. That's one housefly. Okay, but we have 1,000 such equivalent flies. So 1,000 of them then is going to be 10. So now we're going to talk about 1,000 flies. That'll be 10 log base 10 of 1,000 times this. And of course, we're going to use our logarithm math again. We can make this into a sum. That'll be 10 log base 10 of 1,000 plus 10 log base 10 of I over I naught. And I can actually refer to this as, well, actually, continue. So the first term, we're not even using your calculator, really. 10 log base 10 of 10 to the third is 1,000. And I already know what this is. 10 log base 10 of I over I naught, that was a given. That's 40 decibels. Well, we used another logarithm formula. Remember that this power can become a coefficient. So I bring this 3 down, this becomes 30 log base 10 of 10 plus 40 decibels. Log base 10 of 10 is 1. So I have 30 plus 40 decibels. That's equal to 70 decibels. There you go. So one housefly, 10 log base 10 of I over I naught is 40 decibels. 1,000 houseflies, that's 10 log base 10 of 1,000 I1 over I naught, or I can use the math again, 10 log base 10 of 1,000 plus 10 log base 10 of I over I naught. I know this is 40 decibels as given. I can use some, stuff that we know here. 10 log base 10 is 1,000 is 10 to the third. I can use the other formula, from that I gave you for logarithms. Drop the 3 down. 3 times 10 is 30. Then log base 10 of 10 is 1. So I have 30 plus 40 is 70. Okay. That is sound level. So now the next topic, and I believe the last topic of this chapter, is oh no, not quite yet. Next topic of this chapter is going to be what is called the Doppler effect. All right. So Doppler effect, essentially, if you imagine like let's say you're standing in a corner and you hear a police siren. And the police siren sounds like as a police car is coming toward you, it sounds at one pitch, and the police car then goes by you, and it seems like the pitch all of a sudden goes down. But neither one of those pitches is actually the true pitch of the siren. Those pitches are actually changed, or they're actually affected by the velocity of the source, or if you're moving, the detector as well. Okay, that's so this effect is called the Doppler effect. So Doppler effect is essentially this Doppler effect is an alteration in the observed frequency. Of a sound due to motion of either the source, the observer, or both. We'll see the motion of the source and or the observer. Okay, so the pitch of the sound changes due to motion of either the source or the observer. So let's derive what the formulas look like to show what the perceived frequency should be. All right. So first, we'll kind of take two different situations. Well, imagine first of all that the detector is moving and the source is at rest. All right. Detector is moving. And the source is at rest. All right. And so, for instance, the source, we'll say that v sub s is the velocity we give to the source in our derivation, and v sub d is the velocity of the detector. So in an example, the police car, the source is the siren, is the police car, it's the siren on the police car. Your ears are the detectors. Okay. So what's happening here? Well, in this case, source is not moving. V sub s is 0. All right. So V sub s is going to be, so if V sub s equals 0, if I make this my source, there's going to be sound waves that are going to be emanating from this source. All right, so sound waves are emanating from the source. All right, but the source itself, V sub s, is 0. The source itself is not moving. You are moving. Let's imagine that you're moving toward the detector. You're out here, or the detector, V sub d is the detector. So V sub d is, so we're going to say that we're moving toward. So detector moves toward the source. In this particular case. Well, what are we really saying here? Well, essentially the sound waves are going to pass the detector at a faster rate if it's moving toward if it's moving toward it than staying still, right? So more sound waves will pass the detector per unit time if the detector moves toward the source instead of being stationary. See sound waves coming across and seeing the detector world. There's going to be more of them moving by the detector in a per unit time if the detector is heading toward the source than if the detector is actually stationary. Okay, makes sense, right? So mathematically, what does this mean? So let me erase some of this. I'll leave this little picture up. All right, so let us watch the detector. For a time t, all right? And so if it were at rest, the detector were at rest, then what you'd have is just v sub wt over lambda waves would pass by in this time. Right? And so we know that, that basically v sub w is lambda f. F would be the frequency. That's the number of waves per time. If you want to multiply it by the number, you multiply both sides by that time, you get the number of waves, right? So again, how do I know this, right? Because v sub w is lambda f. F is v sub w over lambda, right? That's the number of waves per second. If I want to figure out how many waves in that amount of time happen, I multiply by, if I want the number of waves, I multiply both sides by t. That gives me the number of waves that would pass by me in the time. All right, so I know this. But the detector's moving by as well. So if the detector is moving toward the source at v sub d, then in this same time, v sub d t over lambda more waves will pass by. Right? More waves will pass by. Not just v sub wt over lambda, but an additional v sub dt over lambda from the detector velocity. Remember, v sub d is how fast the detector is moving toward the source. The source is at rest. All right? And so, what do I know? The frequency is the number of waves per time, right? So I'm going to erase this. So I know there's v sub w t over lambda waves because, if it was at rest, and an additional v sub dt over lambda. So the frequency is the number of waves per unit time. We would say this would be the observed frequency. Frequency observed by the detector. The frequency observed by the detector is what? The number of waves that'll go by the detector divided by that unit time. So the number of waves that'll go by the detector, what did I just say? V sub Wt over lambda plus V sub dt over lambda. We're talking frequency now per unit time. Okay, so T's will cancel out, and I can literally get that the observed frequency is V sub W over lambda plus V sub D over lambda. Or remember that V sub W is lambda F. F is the true frequency. Okay, so I can write instead, I can write that lambda is V sub W over F. Again, F is the true frequency. All right, so F obs is equal to V sub W. Again, this is common denominator, so I can actually write this as V sub W plus V sub D all over lambda. Or I can write this as V sub W plus V sub D all over what? V sub W over F. Plug in what lambda is as far as wave is concerned. And now what can I say? Well, I'm almost done. I can just, I can multiply top and bottom of this function by F. So I can multiply the top and the bottom by F. Top by F. I can multiply the bottom by F. Nobody says I can't do that. Right? So I'm just doing some mathematical manipulation. I can write now that F obs is equal to the observed frequency is equal to the true frequency times V sub W plus V sub D over V sub W. So if the siren is going off at a true frequency, and I'm moving toward, let's say, driving toward the siren or whatever, at some speed V sub D, I will hear a higher pitch. So again, so F is, again, this is only for the detector moving toward. It's going to be V sub W plus V sub D over F, over V sub W, sorry. So again, this is a true frequency. This is the speed of sound. This is the speed of the detector. And again, that's the detector moving toward the source. In general, I can write the following. I can actually write the following in general. So in general, I can write that F obs, the observed frequency, is the true frequency times V sub W plus or minus V sub D over V sub W. Okay, and the plus is detector moving toward source. The minus would be the detector moving away from source. So I can actually derive this problem all over again. Instead of the detector moving toward the source, I can actually derive it for the detector moving away from the source. You'd find out that you'd use a minus sign. So I use the plus sign, like you see right here, if the detector is moving toward the source. Use the minus sign if the detector is moving away from the source. Okay, so let's keep this equation highlighted. Again, that is what? Detector is moving, the source is at rest. Well, let's consider a different situation. Now let's let the source move and the detector be at rest. And all right, so different situation. Now the source is moving. The detector is at rest. Okay, so what's going to happen now? Well, the what's going to happen now is that you'll have an effective shortening of the wavelengths with respect to the detector. So if the detector's at rest, here now the detector is going to be, the source is going to be moving. So imagine the source moving, and now the source is going to be constantly firing off these, these waves in a given frequency, but essentially the perceived frequency is going to be affected because the source is moving toward the detector, and essentially what's really going to change is the wavelengths. So if we watch, if we kind of look at the effect. I'll draw a picture here in a minute. The effect, and we'll talk about this the source moving toward the detector, right? So the effect of a source, or the source, we'll say in this case, moving toward the detector is a shortening of the wavelength. In the direction in which the source is moving. Okay, so effectively what is going to be seen, if I can draw this picture well, by the detector in the same picture, if the source is moving toward the detector, then what's going to happen here is the detector is going to perceive a shortening of wavelengths as the detector is moving toward it. So this is the detector, and it's going to appear as if the wavelengths are being shortened. Okay, and let's see why that is. So essentially, let me just erase all this. So let's consider a period t. So let t, which by the way is 1 over the frequency, the true frequency, be the period of the wave. Okay, that's the wave being sent out by the source. from the source. The sound wave, I should say, from the source. Okay, so that's the period. During this interval, during this time interval, all right, the source moves toward the detector. Okay, so he's moving at v sub s. So during this time interval, the source moves toward the detector at distance. He's moving at v sub s of v sub s t. During that period, the source itself is moving at some v sub s t. Okay, and or you can say that's v sub s over f. You're talking about, you know, what the you know, in terms of frequency. Okay, and the wavelength is shortened by that amount. Based upon the actual movement of the source toward the detector. The perceived wavelength is shortened because it is reducing the distance in that time. So the wavelength, I'm going to erase this. All right. So the we now have is that the wavelength, so therefore the wavelength of the sound arriving at the detector what's it going to be? Well, it's going to be, it's not going to be v sub w. Over f, like it normally would be. But it'll be v sub w over f minus the v sub s over f. The wavelength has been shortened by the amount that I described above. All right, and so in this particular case, we have what? The observed frequency is, of course, going to be v sub w over lambda observed, right? V sub w is lambda f. So I'm just basically multiplying lambda down on the bottom. So it's v sub w divided by lambda, the observed lambda by the detector. And I know what that is. That's this. This is lambda observed. V sub w over f minus v sub s over f. So that's going to be v sub w over v sub w over f minus v sub s over f. Can multiply top and bottom by f. I get the observed frequency by the detector will be the true frequency times v sub w over v sub w minus v sub s. Okay. That is for the source moving toward detector. But I want to be more general. And that is, I want to consider the cases of, let's say, the source moving away from the detector. Okay, so let's try to be more general now. So in general, I would say what? Again, I'm talking about source moving, detector at rest. In general, the observed frequency by the detector, that's the person or thing observing, is going to be the true frequency multiplied by what? B sub W over B sub W minus or plus B sub S. And the minus will correspond to source moving toward detector. The plus, in this case, is source moving away from detector. Okay, so I have two different cases. Now I can actually combine everything to make an overall generalized formula by very easily combining the two formulas I just got done deriving. So that's literally a real easy thing to do. And when you do that in the most generalized formula, you get an overall formula that you should always start off with Doppler effect problems. So the general Doppler frequency formula is F observed is the true frequency times, okay? So we have stuff talking about the detector moving, B sub W plus or minus B sub D divided by B sub W minus or plus B sub S, okay? And again, detector and source are both moving. All right. So again, the detector moving toward the source would have the plus sign on top, the detector moving away from the source, the minus sign, the source moving toward the detector, the minus sign, the source moving away from the detector, the plus sign. And how do you tell? Well, you know that if things are closer to each other, their frequency, if they're getting closer, their frequency will increase. How do you make the frequency bigger? Well, you can either make the denominator larger or the numerator smaller. So if you talk about something moving, toward one another, well, the choice would be, well, you do the plus sign to make the numerator of the fraction larger. That makes the fraction larger. Or use the minus sign to make the denominator smaller, which makes the fraction also larger. So again, we'll do some problems to kind of tease this out. Now, these formulas are all good if the speed is if we're talking about objects moving, if the source is moving less than the speed of sound. Okay, so if the source is moving at a source velocity less than the speed of sound, then the above formulas apply. What happens if the source velocity is equal to the speed of sound? What happens if the source is moving so fast that that source is keeping up with its own sound waves? But let's look at the formula. I mean, in this case, like I say, the source is moving so fast that it keeps pace with its own sound waves. You know, so, and then of course the formula that we had for a moving source, remember this? F is F observed is the true frequency times speed of sound divided by, we'll say, speed of sound minus or plus v sub s. Well, if I make v sub s, this is say I consider the case where the sound device is going toward you. If I make v sub s equal to v sub w, then I have a divide by 0. And so that divide by 0 is illegal. You can't do that. So you know, you divide. So if v sub w equals v sub s, you have a divide by 0 problem. That's illegal in mathematics. You cannot divide by 0. So basically, these equations are no good. Equations that we derived are no good if the source speed is equal to or greater than the speed of sound. All right, and so we refer to this as a supersonic condition. All right, so if v sub s is greater than or equal to v sub w, then the above formulas, the above Doppler formulas do not apply. They're invalid. This condition is called supersonic. All right, and so what you actually have is you hear a sonic boom. Literally, the object will be going through the air through the waves, creating a shock wave. And so the shock wave is what you actually perceive. It's a sonic boom. There's actually for an airplane, there's actually 2 of them. You have the one from the front end and one from the back end. So when you hear sonic booms, that's what's happening is the aircraft is actually faster than the speed of sound. Okay, and so what happens now is that, well, now the source is exceeding, you know, its own sound waves, and so what you end up having is you develop what's called a Mach cone. So in supersonic flight, or for supersonic conditions, there is a development of what's called a Mach cone. named after Ernst Mach. Austrian physicist. Mach cone. Let's imagine here that, how do I get this? So let's just say, here's the source. And the source is moving along at a speed greater than the speed of sound. So the source, as it moves along, let's say back in this, let's say right now the source is way up here. Okay, the source is way up here, and the source is just generating a sound wave. All right, barely. Back here, that sound wave generated by the source might be, let's say, this big. And back here, that sound wave may have been allowed to expand out to this large. And maybe here, it's expanded to be this large, and maybe finally here, it is this large. And so what we actually have is you draw a line tangent to the circles, you get a cone. This cone has an angle theta. So this angle theta is this angle right here. And that's called the Mach angle. This half angle is the Mach angle. Okay, so if you imagine that all of these speeds are all v sub w. So each of these radius, basically this circle is expanding out. This wave is expanding out at v sub w. Basically, it's expanding by the speed of sound. And yet, the source is moving at some v sub s that's greater than the speed of sound. And so it's leaving these sound waves behind, and these sound waves are growing in the past. And so here's as the past we get closer to the present, there's not as much time for these sound waves to actually expand. And so what we actually see here is that a distance here might be v sub w times t. The distance for this circle, and we can then say that the we can make the sine of the angle of this triangle. Again, this is going to be basically this is a right triangle. This is a tangent line to the circle, so this is a tangent line. So it means this forms a right triangle, and this would be v sub st. So in a given time, this source is moved all the way over to here, v sub s times t. Again, this is velocity times time, whereas the sound wave is only expanded out this much because the source is actually moving faster than the speed of sound. And so to find the angle, it's simply the opposite of this half angle, theta, divided by hypotenuse. So v sub w t over v sub st, or the t's cancel out. So you really get that the sine of theta is v sub w or v sub s. And this is the Mach angle. This is the half angle, not the whole angle, but the half angle. Again, if I took this cone, half of the angle of the cone is this theta. This theta, again, is the Mach angle, is the half angle. And this is the opposite, the radius, over the hypotenuse, which is the distance that the source actually traveled. We also define what is called a Mach number. Mach number is basically the ratio of the source speed over the speed of sound. So typically we'll talk about Mach numbers. Mach number is the ratio of the speed of the source over the speed of sound. So if you're going Mach 1, you know, speed of source is the speed of sound. Mach 2, you're going twice the speed of sound. Mach 3, 3 times the speed of sound. Okay? All right, so let's do some Doppler effect problems. Let's go back to the subsonic. OpenStack 17.30. What frequency is received by a person watching an oncoming ambulance moving at 110 kilometers per hour and emitting a steady 800 hertz sound from its siren. Okay, that's yes, that's A. All right, and then B says, what frequency does she receive oh, sorry, I missed something. The speed of sound on this day is 345 meters per second. Okay, important piece of information. B, what frequency does she receive after the ambulance has passed? Okay, so that's B. So what frequency is received by a person watching an oncoming ambulance moving at 110 kilometers per hour and emitting a steady 800 hertz sound from its siren? The speed of sound on this day is 345 meters per second. B, what frequency does she receive after the ambulance has passed? Okay, so note that down. Go. So ambulance is going to come toward this person, part A. So the ambulance is moving toward the person. So we know that we start off with the generalized formula. F observed is the true frequency times V sub W plus or minus V sub D over V sub W minus or plus V sub S. And that is a generalized Doppler formula. Okay, we know a few things. The speed of sound is 345 meters per second. We know that. We know that V sub D is 0. The detector does not move. That's the person listening. Okay? And we know V sub S, but we got to put that into SI, meters per second units. So V sub S we know is 110 kilometers per hour. That doesn't do us any good. We know there's 1,000 meters in a kilometer. Kilometers cancel. And an hour has 3,600 seconds. So the speed of the source, the ambulance, is 30.56 meters per second. And the frequency, the true frequency of the siren is 800 hertz. That's the siren. If everything was stationary, that's the frequency you would perceive, the true frequency. So in part A, we notice that the ambulance is going to move toward her. And so again, what's going to happen here is that we can fix this formula up. We know that V sub D is 0. So the formula can get fixed like this. And now we're looking at the ambulance moving toward her. In that case, if that's the case, moving toward means minus. And moving source moving toward the detector is minus, source moving away from the detector is plus. So we can fix that formula up there with that information. And then we can pretty much do the problem. In this case, we'd say, well, F observed is going to be the true frequency, 800 hertz, times what? Well, we have speed of sound is 345 meters per second divided by speed of sound minus source velocity. 345 meters per second minus 30.56 meters per second. We find out that the observed frequency, she should observe a higher frequency, will be 878 hertz. So she will perceive the siren as having a higher frequency than what it does. Instead of the 800 hertz that it truly has, she will perceive it to have 878 hertz. She'll perceive a higher frequency. Now, after the part B, the siren, the ambulance is now passed. Now the ambulance is moving away from her. In that case, she's still standing still. The detector V sub D is still 0. Now I turn that into a plus. And so everything's the same except this is now a plus. If we do it now, you get 735. Now she perceives a lower frequency than what is really true. Okay, so again, that formula, I'd have to put a plus in the bottom. All right, I'll let you take a moment to copy that. All right, and again, that is now part B. All right, I'm going to do OpenStax 17.33. All right, this says a spectator at a parade. Receives an 888 hertz tone. from an oncoming trumpeter who is playing an 880 hertz note. Okay. At what speed is the musician approaching this? Approaching. So at what speed? Is the musician approaching? If the speed of sound is 338 meters per second. Okay. A spectator at a parade receives an 888 hertz tone from an oncoming trumpeter who is playing an 880 hertz note. What speed is the musician approaching if the speed of sound is 338 meters per second? Okay, so you have a stationary detector, the spectator, and you have a moving musician. And the musician is moving toward the spectator. Okay. So again, what are we told? Well, we're actually given the observed frequency is 888 hertz. We know the true frequency, that's given to us too, is 800 hertz. Okay. We know the speed of sound on that day, 338 meters per second. These are all givens. Since the spectator's at rest, V sub D is 0. The detector, or the spectator, if you will, is at rest. And the trumpeter is going, we don't know the trumpeter, but again, the trumpeter is moving toward the spectator. So again, we start off by looking at we always start with the most general form of the Doppler formula. So that's F observed is the true frequency times the speed of sound plus or minus V sub D, detector velocity, divided by the speed of sound minus or plus the source velocity. We always start with that. Then we simplify. Well, we know the detector is standing still. So the detector is 0. There's nothing there. V sub D, so erase that. That becomes V sub W on top. And we're assuming the trumpeter approaches the detector, or we're told that. So this becomes a minus. When the source approaches the detector, then you use a minus sign. So fixing this up. What we want is we want to find the velocity of the source. So we have to come in here and figure out what V sub S is. All right, so it's a little bit of algebra that has to be done. So I think the best thing to do now is I'm going to divide both sides by F. So I have F obs over F, okay, is going to be V sub W over V sub W minus V sub S. All right. And I'm going to continue my algebra up there. All right. I'm going to flip both of the equations. I can do that. So I can write F. Actually, what I'm going to do is I'm going to do this. I'm going to flip them about the equal sign first. So V sub W over V sub W minus V sub S is F obs over F. Okay. Now I'm going to flip both equations about the equal sign. So another. I can do that too. So this becomes V sub W minus V sub S over V sub W is F over F ops. Just flipping about the equal sign, I can do that. Nobody says I can't. And I'll multiply both sides by V sub W. So I get V sub W minus V sub S. Since I multiply both sides with V sub W, the V sub W cancels out on the left side. I'll just do it right here. Multiply both sides by V sub W. All right. And if I do that, I get V sub W minus V sub S, so they cancel. And I get F over F ops times V sub W. And then finally, I can just put V sub S over here, subtract off. I can solve for V sub S right now. V sub S is now going to be V sub W minus F over F obs V sub W. All right. Or I can extract out V sub W. I have V sub S is V sub W times the quantity 1 minus F over F obs. And I'm ready to put in how fast the trumpet is coming. So V sub S is the speed of sound, 338 meters per second. Times the quantity 1 minus the true frequency is 800 hertz. The observed frequency is 888 hertz. And I find out that the trumpeter is approaching the observer at 3.05 meters per second. Okay, again, using the Doppler effect. Okay. The last topic I want to talk about is kind of a continuation of the concept of resonance and interference. We talked about string instruments before. Now we're going to talk about instruments that deal with columns of air, like a flute or a clarinet or a trumpet. All right, and so again, how does that work? So sound interference and resonance. Okay. So the idea is, let's imagine that I have a tube that's closed at one end. So consider a tube of air closed at one end. Okay, so I have this tube. And I'm going to put a pitchfork, or I'm sorry, tuning fork right out front. Let's imagine here that instead I can vary the frequency. So let's imagine I place a variable frequency. Tuning fork at the mouth of the tube. So this tuning fork doesn't just have one frequency, it varies. And I start turning up the tuning fork, or whatever, this frequency generator. Normally, at first, I'm not going to see any kind of sound from the tube. All of a sudden, I'll get a very loud sound. So as we increase the frequency, of the frequency generator or the tuning fork, we do not hear much sound from the tube. And then suddenly at a certain frequency, or at some frequency, we hear a loud sound. From the tube. So you're turning up and turning up the frequency, and you're basically causing disturbance of airwaves or sound waves in air, and they're going into the tube. Those waves, basically the wave comes back, and at some point, what's happening is you finally find a resonance where you see the first situation where, just like with the wave in a string, where the air or the wave, the sound wave, constructively interferes with itself. Okay, we'll find that in this situation, because this tube is closed to one end, there must be a node on the back of the tube. There must be a node there. And so what you've done is you've found a situation where the waves, the sound waves, will actually that are leaving the tube are constructively interfering with the sound waves that are emitting from the tuning fork. So you have a situation where you have a node at the back and an antinode at the mouth of the tube. Okay, and so you have a node in the back because the air can't go, the sound waves can't go anywhere in the back. The antinode, remember, is the maximum amplitude. So this is an antinode. Okay, so again, this is a column of air. It is a tube close to one end, like a clarinet or like a trumpet. And it's a situation where the sound waves are constructively interfering with themselves. And so you have a maximum, you have a maximum interference, a maximum constructive interference, which we call an antinode or amplitude. So let me write this out. So the sound waves reflected off the back of the tube constructively interfere with the sound waves entering the tube. So again, a lot of the nomenclature is the same. You have an antinode in the front at the mouth of the tube and a node in the back. Why is the node here? Because the closed tube causes a node. The air can't go anywhere. The fact that it's closed back there means that there's a node there. All right, and so if I imagine this tube to have a length L, and there's a length L in this tube, well, if you look at this, this is a quarter of a wavelength. I mean, if you want the whole wave, you'd have to, I mean, if you construct the entire wave, you'd have to allow for what? It to come down like this, and then to entirely have an entire new wavelength. And this is not drawn well, but you get the point. So what you have here is only a quarter of a wavelength in this situation. So in this case, whatever your lambda 1 is, you know, your lambda 1 is going to be the entire wavelength, but L is equivalent to 1/4 lambda 1. That's your fundamental wavelength of your wave. And that means that lambda 1 in this particular case is 4L. Okay. So this would be the fundamental situation, your situation where you found a frequency that has the that has the first resonance. This, of course, is called a resonance. So what we have here is a resonance, just like the wave on a string. So let's kind of draw some pictures. And this is a wave, this is a tube closed to one end. So we're talking about a tube closed at one end. Like, you know, examples would be like a clarinet. Another example would be a trumpet. Okay. And so we see initially, let's draw some pictures here. Here's the tube. Okay. Has a length L. We have a node in the back. Antinode. We know that this is 1/4 of lambda 1. So quarter of a wavelength. We just got to determining that lambda 1 is 4L. And of course, we know the frequency is always going to be what? The speed of sound divided by lambda. In this case, what is lambda is 4L. So it'll be the speed of sound divided by 4L. If we're talking about 1. You know, this would be the fundamental frequency. Or the first harmonic. Same terms as before. What we know, though, that if we continue increasing the frequency of the input frequency generator, you know, this loud sound will suddenly go away, and then nothing will occur until you get to the next special frequency, and then you'll get your next resonance. Well, what happens then? Well, again, you always have to have an antinode at the end. So your next situation would be something like this. I always have to have a node at the back, but now I'm going to have a node in the middle and an antinode at the end. So I'm going to have like this. And what I'm going to have here is basically, this is 3/4 of a wavelength. I mean, if I were to continue it out here, I'd have the extra quarter. So again, this is still a tube of length L. But this is going to be 3/4 of this next wavelength, lambda 2. All right, and so what do? Well, I say that basically lambda 2, so L equals lambda, or L is equal to 3/4 lambda 2, which implies that lambda 2 is going to be 4/3 L. And that implies then that F2 will be 3 piece of W over 4L. So again, I'm going to divide by lambda 2, and then divided by 4/3 is the same as multiplying by 3/4. This is the first overtone. Or the second harmonic. Okay. And I can continue. I can take the frequency generator, continue increasing the frequency. The waves in the tube will go away. And finally, I get the next situation where I have a resonance. And how can I construct that? Well, I draw the same tube. Okay, now what? Well, I have to have a node in the back. Now I have 2 nodes. So I'll have there you go. So that's a whole wavelength there plus a quarter. So I still have a length L. Now I have 2 nodes. I must have an antinode at the mouth of the tube. So this comes out to be a whole wavelength plus another quarter. That's 5/4. 1 plus a quarter is 5/4. So 5/4 lambda 3. Okay, that's so essentially L. That length is the same as 5/4 lambda 3, or lambda 3 is 4/5 L, or F3 is 5V sub W over 4L. And we would call this what? The second overtone. Or the third harmonic. Okay. And so I can continue doing this forever, essentially. I mean, I can go on and continue figuring out ways of putting nodes inside of this tube close to one end, such that I have an antinode at the mouth of the tube. We can continue doing this, but in general, what we would find out is that we can have a generalized formula for this. I'm going to erase all this, and I'll have a generalized formula now for tube close to one end. I think we have enough to see a pattern. So tube close to one end would simply be F sub n is going to be n V sub W over 4L. and n is limited to the odd integers, 1, 3, 5, dot, dot, dot. Okay, so again, 1 would correspond to the fundamental, 3, the first overtone, or sorry, the second overtone, or second harmonic, third overtone, or third harmonic, so on and so forth. So again, as you saw, that's the general formula. So if I want to keep on drawing these, those would be my frequencies. V sub W, of course, is the speed of sound. Okay, so again, this is now interesting here is that the resonant frequencies depend on the speed of sound and hence the temperature, right? So if you look at this, the resonant frequencies depend on the speed of sound and hence the temperature. We know the speed of sound depends on temperature. So if you notice, many musicians do not play their instruments until they warm up. To room temperature. Otherwise, the notes aren't going to sound right. This is another problem if you have organs inside of heated cathedrals or unheated cathedrals. Again, there is the temperature, the speed of sound that is important to this. So again, another would be, a problem. So another problem would be, problem with organs in unheated cathedrals. Okay, so that's another, problem with this temperature dependence on the speed of sound, and of course, the speed of sound, the frequencies, the resonant frequencies depend on the speed of sound. Okay, now what happens, on the other hand, if you have a tube that's open at both ends? So now we'll go with other instruments, for instance, like a flute or an oboe. So now we have air in a tube open at both ends. Example, flute or an oboe. Okay, tube open at both ends. Well, we have to play the game of figuring out how to fit in the frequencies, the resonant frequencies. So I'd want to find a way to have in a fundamental case, in a minimal case, I must have an antinode at both ends of this tube. So now I have a tube that's open at both ends. Okay, length L. A little bit bigger. Open at both ends, and it has a length L. want to have an antinode, so I can stick a node in the middle. Have an antinode on each end. That's one way of doing it. If you look at that carefully, that's a half a lambda. Quarter here plus a quarter there. So this is 1/2 of lambda 1 fundamental wavelength. We play the same game. L is lambda 1 over 2, or lambda 1 is 2L. So that means that in this case, I'd have F1 would be basically V sub W over 2L. In this particular case, that's my, again, this is my fundamental, or my first harmonic. Well, in the next case where I have antinodes at both ends, well, I have 2 nodes. So I have an antinode and so what is this? Well, that's half plus a quarter is 1. All right, so here's L, and this is literally lambda 2. Oh, I can fit a whole wavelength in there, or equivalent thereof. So that means that lambda 2 equals L, and my F2, again, is always V sub W over lambda. When that, no lambda 2, that'll be just V sub W over L. And so again, this would be what? This would be the first overtone, second harmonic. One more time, how can I play the game to have antinodes at both ends? Well, let's see, I'll put, I guess, 3 nodes in now. All right, so what do I have now? I have a full wavelength right there, and then 2 extra quarters make a half. That's 3 halves. So basically I have that, here's L, same tube. Now this is 3 halves, lambda 3. So F3, or let's write this out. So L is 3 halves lambda 3, or lambda 3 is 2/3 L. All right, so playing the same game, F3 is the speed of sound divided by lambda 3. Well, again, divided by 2/3 is the same as multiplied by 3 halves. So I would have 3 halves V sub W over L. So I have 1 over 2, basically 1 over 2, 2 over 2, 3 over 2. So you can kind of get the pattern of what the overall general pattern should be. So in general, and again, this would be what? This would be the second overtone. Or the third harmonic. Okay. And you see the nomenclature. All right, so in general, tube open at both ends. Looking at the pattern, you can say in general, F sub n would be n B sub W over 2L, where n is 1, 2, 3, so on and so forth, all the integers, positive integers. And that's a tube open at both ends. Use that formula. Tube closed at one end, use the previous formula. All right, so let's close this off by working some problems. So we'll start with OpenStack 17.38. That one says a showy custom-built car. I guess they put that in quotes. Has two brass horns. That are supposed to produce the same frequency. But actually emit 263.8 and 264.5 hertz. What beat frequency is produced? Okay, so what do we know? Well, again, so a showy custom-built car has two brass horns that are supposed to produce the same frequency, but actually emit 263.8 and 264.5 hertz. So they're a little bit different. What beat frequency is produced? So we know that F1, we'll say, is 263.8 hertz. F2, 264.5 hertz. The beat frequency, F sub beat, is the absolute value of F1 minus F2, or the absolute value of 263.8 hertz minus 264.5 hertz. The beat frequency will be 0.7 hertz. Okay. Do 17.40. All right, OpenStacks 17.40. What beat frequencies? result if a piano hammer hits 3 strings that emit frequencies of 127.8, 128.1, and 128.3 hertz. All right, so we have to consider each difference, you know, so we have an F1, F2, and F3, for instance. So let's let F1 be 127.8 hertz. F2 be 128.1 hertz. And F3 be 128.3. All right, so I have 3 possible beat frequencies. The one dealing with F1 minus F2, the absolute value there. F1 minus F2, that would be the absolute value of 127.8 hertz minus 128.1 hertz. That becomes 0.3 hertz. That's 1 beat frequency I can see or perceive. Another one, F1 minus F3. That would be 127.8 hertz. Absolute value of that minus 128.3 hertz. That would be a beat frequency of 0.5 hertz. And finally, one more possible beat frequency, 2 and 3. So let's see if I can stay in the camera here. The absolute value F2 minus F3. That would be the absolute value of 128.1 hertz minus 128.3 hertz. That would give me 0.2 hertz. So every possible combination of beat frequencies, not just 2. All right, that's all listed that problem. Okay, 17.42, open stacks. All right, see what this is about. 17.42 says, what is the fundamental frequency of a 0.672 meter long tube open at both ends on a day When the speed of sound is 344 meters per second. Okay. What is the frequency of its second harmonic? So this is A up here. B. Let's see. This first part is A. Okay. B is yeah. What is the frequency of its second harmonic? Okay, so so we have a formula for the tube open at both ends. Let's start with it. Remember the tube open at both ends. F sub n was n v sub w over 2L. And this is a tube open at both ends as specified. Okay. Let's see. Speed of sound, v sub w, is 344 meters per second, and the length of the tube is 0.672 meters. I want the fundamental frequency. Fundamental frequency occurs, so fundamental frequency occurs for n equals 1. All right, and so F1 is going to be 1 times v sub w over 2L, or I can call it specific. So it's 1 times v sub w over 2L, or v sub w, let's see, 1 v sub w over 2L. V sub w is then 344 meters per second divided by 2 divided by 0.672 meters. And I find out that F1 is equal to, when I do that, 256 hertz. So that is the fundamental frequency of this tube. Okay. Now I want the first overtone. Well, the first overtone means that's the next one, right? So I know that n for the tube open at both ends, n goes as 1, 2, 3, so on and so forth. So my next one would be putting a 2. So why don't I just multiply? Well, I want F2, I'll just multiply F1 by 2. So F2 is just 2F1, right? Which is 512 hertz. That's the answer to part B. First harmonic is the next one, so that's the next one in the series. And remember, the tube open at both ends, n can be 1, 2, 3, so on and so forth, right? So n can be every number. Be careful if it was a tube open at one end, n can only be odd integers, all right? So again, be careful what you're doing. All right, that's the last thing I'm going to do one more thing for one more problem for this video, and that's it. So here we go. I'm going to do OpenStack 17.45. Okay, open stacks. 17.45. How long must a flute be? In order to have a fundamental frequency of 260 hertz. This frequency corresponds to middle C on the evenly tapered chromatic scale. On a day when the speed is when an air temperature is 20 degrees Celsius. So again, it is a tube open at both ends. All right, so question. So open test 17.44. How long must a flute be? In order to have a fundamental frequency of 260 hertz, this frequency corresponds to middle C on an evenly tapered chromatic scale. On a day when an air temperature is 20 degrees Celsius, the flute is a tube open at both ends. Okay, so let's do this. So the formula, again, for a tube open at both ends, the formula we want to work with is F sub n is N, B sub W over 2L, where N equals 1, 2, 3, so on and so forth. Again, this is a tube open at both ends. Okay, so I want to use that formula. The fundamental frequency is what we're given. So we're given that F1 is 262 hertz. And that is the fundamental frequency. That's given to us. All right. And so the temperature is 20 degrees Celsius. Well, the speed of sound in air, remember, is 331 meters per second. Again, this corresponds to 293 Kelvin. 331 meters per second is a square root of 293 Kelvin over 273 Kelvin. Square root, speed of sound, as we recall, is 343 meters per second. But again, that's why they gave you the temperature. All right. And the question is, what is L? Now I know the speed of sound. I know the fundamental frequency. Now that I know all these, I can solve for L. So again, what I want here, this formula becomes F1 is 1 times V sub W over 2L. It's fundamental. That means that L is V sub W over 2F1. That's what I get. L is 343 meters per second over 2 times 262 hertz. All right, and L is right here. L then becomes, at this point, I worked out the math, 0.655 meters. Which equals 65.5 centimeters. That's how long the fluid has to be. All right, so in the little glare here. So L is 65.5 centimeters. That's my answer. That is it for this video and chapters 16 and 17.